prior to the SR20 for supplemental safety.
I think there is some disturbance in the screen sharing.
I could not see him on the screen.
Yeah.
Some problem, I think.
Mr. Krishnalok is there? Krishnalok is online.
Pardon me, please.
Mr. Krishnalok, the author who is presenting, is he still connected?
Nothing is to be seen here. I think technical session 2 only is being seen.
Yeah, screen is not visible, and he's yeah, he is logged out. Probably some problem with his connection. No, it is.
So should we wait for him to relog in, or should we go with the
Probably we can proceed with the next speaker.
next paper, no? Yeah.
Yeah.
So our next paper is on experiences with deterministic and Central. You can just tell me the order.
Yeah. Okay. The third speaker, Dr. Balaji Rao, is your author, co-author is already available now.
Yeah, right now he is having some problem. Yeah, I think he will come back. He will come. The other
Okay,
thing,
then,
he can go ahead.
Okay, then the third talk is by Shaino Ramachandran.
Archana Yadav is connected, so.
Okay, then we can start
Seeing
with
her.
yeah. Can we start with Archana Yadav, A38?
Yeah.
Yeah, please go ahead, madam.
No, actually, my student is presenting here. Hello?
Yes, sir.
I think he has come. Can you go ahead?
Okay, then we can start with this paper 1, that is A01. Madam, is it okay?
Yes, it is okay. You
Yeah.
with Mr. Balaji Rao's paper.
Yeah.
Go ahead, Jagan. You please present.
Sir, okay, sir. Okay, sir. So, sir, screen is visible, sir.
Yes, it is visible and you are
Okay. Thank you, sir. Thank you, sir. Sir, respected dignitaries, directors, and co-participants of the program. A very good afternoon, good evening to all. My topic, and I'm very much thankful to my guides, Dr. Balaji Rao sir and Dr. Desai sir, Bhaskar Desai sir, for giving opportunity to present this to the today's program. And my topic is probabilistic analysis of mode to fracture energy of a sustainable concrete. In order to realize and promote the sustainability in the construction of concrete structures, it is important to explore the possible alternatives for the cement, because the production of cement delivers a large quantity of carbon dioxide into the atmosphere, polluting the environment. So in this concern, the possibility of using fly ash is a suitable partial replacement material for cement was considered, and an experimental investigation was done along with the mode to along with probabilistic analysis for mode to fracture of fly ash based concrete. So fly ash is utilized in partial replacement for cement in my experimental work, and probabilistic analysis was made for the mode to fracture of fly ash based concrete. And in certain design situations, it is important to know the shear resistance capacity of the concrete, and understanding of the mode to fracture of behavior of concrete is an important one, because out of all the three modes, mode 1 and mode 3 will give the indications before failure. But in the mode 2 is a very suddenly occurring type of failure, which is causing a catastrophic failure, especially in the case of flat slabs and footings. That is, the punching shear behavior is a catastrophic one. From the literature, it is observed that all the earlier works related to fracture mechanics are related to mode 1. In the mode 1, some of them are given by Bajant and Beggerodin, the probabilistic analysis on mode 1 fracture. But they have done with plain concrete only. And some and the other one is G. Apparao and B. K. Raghuprasad, mode 1 fracture energy of plain concrete. And some other is Chung Ho Yu et al. In mode 1 fracture energy, but they have used fly ash as a partial replacement for cement. That is related to mode 1. These three are related to mode 1. And in the related to mode 2, only plain concrete was considered in the earlier researchers. They are dominant. The more prominent one are given by Prakash Desai and B. K. Raghuprasad and V. Bhaskar Desai in mode 2 fracture of concrete only. And another one is Reinhardt and Zhu of mode 2 fractures of. These are the plain concretes only. So in the present experimental investigation, fly ash based concrete was considered for mode 2 fracture of concrete, considering the fly ash as a partial replacement in the percentages of 0, 5, 10, 15, 20, and 25, and 30% by mass, replacing the cement in concrete. And mode 2 fracture energy was calculated. And based on this experimental investigation, a probabilistic analysis was done to characterize the mode 2 fracture energy of fly ash based concrete. So for this, DCN specimen was considered, which is suggested by the Prakash Desai et al. And Bhaskar Desai to study the mode 2 fracture behavior, which they have done for plain concrete. So this is the specimen shape, this one. In this experimental work and probabilistic analysis, we have considered a cube of 150 mm size, and two slots are made, varying slots, that is A, 45 mm, 60 mm, 75 mm, and 90 mm. And these are the two supports at the bottom. And this is the load occurring. So it is going to represent a true behavior of a footing or a flat slab, the punching behavior. So this is the front view of the specimen. And this is the bottom view. These two are the supports. And this is the top view of the specimen where the load is coming. So this represents the load. So this is the top view of this specimen. And then after testing, load displacement calculations, load displacement observations are made for this one. And these are the crack patterns for a sample of specimens with these three are the plain cubes. Crushing strength also considered, split tensile strength was also considered. And these are the crack patterns with the A by W ratios. A is the notch depth and D is the total, W is the total depth, that is 150 mm. So A by W ratios are 0.3, 0.4, 0.51, 0.6 are considered. So these are the crack patterns. And from the load displacement relations, the graphs, considering the average load displacement relation, this is the graph related to the load displacement relation. In this one, first crack was in crack initiation load was observed, and also the ultimate load was observed. The area under the load displacement graph was calculated, and the fracture energy, experimental fracture energy in mode 2 fracture is given by area under the load displacement curve divided by shear resisting area. Shear resisting area, this is the ligamental areas resisting the shear above and below the notches. This area was calculated, and find out mode 2 fracture energy was calculated by experimentally. So it involves the costly one for going the experimental observation. So probabilistic analysis was made. And for this, a trilinear graph considering the two portions in up to first crack, that is PCR. So PCR by 2 slope, there is a substantial change in the slope was observed here. PCR by 2 to PCR, first initiation crack load. And then this is the ultimate load. So the trilinear graph was plotted for this one. And from this trilinear graph, the stiffness corresponding to the three linear portions, that is the slopes, K1, K2, K3 are considered, and the constants intercepts C2 and C3 for the second one and third one. Slopes are considered, third one straight lines are considered for evaluate the different for all the A by W ratios and percentage replacements considered in this experimental work. And in the probabilistic analysis, first crack and ultimate load and K1, K2, the slopes of the straight lines considered as random variables. Considering the mean values and COV of these variables, first crack load and ultimate load, K1, K2, K3, that is the slopes of the lines, trilinear plots, as considered as random variables. And the probabilistic analysis was done, and COV of that variables was found out. Considering mean values of this probabilistic analysis and assuming the values of PCR, that is the crack initiation load, ultimate load, K1, K2, K3 are considered as 0.5, 0.1, 0.15, 0.5. For the probabilistic analysis was done using Monte Carlo simulation approach, and 10,000 cycles was considered for this, and generation of 10,000 samples for the basic random variables. The 5 variables are considered as the crack initiation load, ultimate load, slopes of the lines for a given combination of percentage replacements and A by W ratios. So considering these deformations at loads PCR by 2, PCR, this is the of the crack initiation load, and ultimate load. D1, D2, D3, or C2, C3, that is displacements and constants on the intercept, that is intercepts on the y-axis, that is loads are considered, and P delta curve is drawn for each combination of load. So this using the conditions used are these are PCR should be less than PU, that is the crack initiation load should be less than ultimate load, and the slopes of the second portion, that is PCR by 2 to PCR, is less than slope for the it is more than the slope for K3. K3 should be less than K2, and K2 should be less than K1. So K1 is the slope for 0 to half the crack initiation load. K2 is the slope for half the crack initiation load to the ultimate crack initiation load, and K3 is the slope for crack initiation load to the ultimate load. And from the experimental observations, the displacement ratios D2 by D1 and D3 by D2 should be less than 14. These conditions are given for the generation of load displacement variations for 10,000 cycles. The area under this trilinear plots are calculated by summing of the 3 segmental areas. That is below the curve, 0 to PCR by 2, and then PCR by 2 to PCR, and then PCR to PU, ultimate load. So after the calculation of this, this area divided by the shear resisting area will give the fracture energy in mode to this one. And using the results of this simulation, each combination is considered statistical properties of the fracture energy, that is the mean, COV, skewness, and kurtosis are estimated. Also, the information about the frequency distribution of the probabilistic fracture energy G2F is obtained for all the percentage replacements and A by W ratios considered. This is one of the sample graph, the fracture energy on y-axis, fracture energy on the x-axis, and frequency on the y-axis. So this is the plot, and this is tested for which type of distribution is going to follow. So it both log normal distribution and normal distribution are plotted to the variations. And it is observed from this graph, it is observed that for all the graphs, log normal distribution is going to be valid. And from the probabilistic analysis, so for different percentage variations of replacements of cement with fly ash, up to 30% variations for different A by W ratios, so fracture energies are probabilistic fracture energies are calculated, and minimum values of this for a particular replacement also considered for all the A by W ratios, and maximum values, and the mean values also calculated. So these are varying from 1495.76 Newton per meter to highest is 2004 Newton per meter. So an attempt is made to fit the goodness of fit for the normal and log normal distributions. That is, it is going to follow the log normal distribution here. The log normal distribution is the green line, and the blue is the observed frequency. So these two are coinciding. This is same for all the variations considered. And normal is slightly mismatching with the observed frequency. So based on this characteristic fracture energy was calculated using this relation. And then for the mean values observed from the probabilistic analysis, So mean fracture energy, a suitable curve is plotted for this one, for the observed fracture energies by probabilistic analysis. So that is given by this relation. G mean value of fracture energy. This is a second degree curve. This is the relation. And this is the graph showing the characteristic fracture energy, this one with the red line. And this is the experimental minimum fracture energy. So characteristic fracture energy lies above the experimental minimum fracture energy. So this is the proposed equation for finding the fracture energy of fly ash based concrete for any percentage replacement of cement with fly ash. So this is the experimental work done during my PhD program. The guides Dr. Bhaskar Desai sir and Dr. Balaji Rao sir. So thank you, sir.
Dr. Sendil?
Okay, thank you.
Yeah, madam.
Thank you. We can go to the next presentation. Can we continue with the presentation of two-seater aircraft, whether he has come online?
Mr. S. Krishnalok, if you are online, please respond.
Yeah, then we can complete his presentation, I think.
Yeah, but he's not seen around.
It looks like he's not online.
Okay, Jagan, you have to unshare the screen.
Okay. And Mr. Shaino Ramachandran, if he's there, we can continue. That is the third paper, A09.
Yeah, that's the experiences with deterministic safety. And,
Yeah.
Yeah. Okay. So if Shaino Ramachandran is there, we can.
Mr. Shaino Ramachandran, are you there? Please say hi. I think he's not around.
Yeah.
Then Mr. M. Bose, I saw him online.
Hello.
Yeah.
Yeah, I am here.
Yeah, so I think now we can have the paper on Hazov, I think. Yeah, paper. No? Hello.
I am just connecting to sharing the screen.
Okay. So, okay, Mr. Bose, you can. So we will hear from Mr.
Is it
Bose
visible,
now.
madam? That my PPT.
No, your screen is not come up.
Yeah, your screen has not come up.
Please wait. Is it coming now?
It is started screen sharing, but still not visible.
Maybe it's taking time.
Yes, it has come.
Yeah, now
It has
okay,
come, no?
so then now, Mr. Bose, we will hear from Mr. Bose regarding hazard and operability Hazov study. So come, you can start, Mr. Bose.
Good evening, all. I am from Brit. I am Bose, and I am presenting a paper on hazard operability.
You are on mute.
Mr. Bose, your audio is not there. And your page is stuck on the first keywords. Hello.
I think
Hello.
Yes.
Am I audible now?
Yeah, now you are audible. Please go ahead.
Okay. The keywords of this paper, it is listed here. It is introduction, historical background, processor and objective for Hazov study team, methods of Hazov studies, guide words, Hazov team composition, Hazov methodology, benefits of Hazov study, and finally conclusion. When we talk about introduction, here hazard analysis means identification of undesired event which lead to the minimization of hazard, analysis of by which such undesired events could occur, and estimation of the extent, magnitude, and likelihood of any harmful effects or consequences. Here I am focusing two part. It is one is hazard and hazard. Second one is hazard. Hazard analysis and it is hazard operativity study. When we talk about hazard, it is generally undertaken at the preliminary stage. In case of determining location, like when we set up some new plant and all, so we need to identify the location whether this plant which we are going to have is having proper connectivity, availability of water and electricity, transport arrangement, land, proper land, whether it is agricultural, non-agricultural, all those things it covers in this determining the location. Then basic design principle and operational parameters to establish the adequacy of basic safety design. Next is the operation and the environmental control. Undertaken by professional team with expertise in failure mode of and effect analysis. These are the four few analysis I have listed here. It is fault tree analysis, simulation and modeling, event tree analysis, and consequences analysis. These are all the very important analysis we undertake when we go for hazard. When we talk about hazard, a sub-study is defined as application of a formal systematic critical examination to the process and engineering intentions of the new facilities to assess hazard potential of operation or of the individual items of equipment and the consequential effect of facility as a whole. Hazard studies are normally undertaken at any advanced stage of project implementation when the design criteria are well established. The study can be used for both new and working plans. They have to be carried out by multidisciplinary team of experienced technical personnel having detailed knowledge of both the design and operation of the plant. Here, what we have to take care is that person who comes into the team, their qualification, that is adequate qualification they should have first. Second is that experience, how much experience they put in. So then these people can only pinpoint the various hazards. A preliminary hazard study is intended to review the general parameters of material processed, unit operation, and layout of individual unit and plant subunits. Detailed hazard study is required after a finalization of the design to identify the potentially hazardous situation and to arrive at an agreeable option to rectify the design deviation and anomalies. Hazard is any existing or potential condition in the workplace, which by itself or by interacting with other variables can result in the unwanted effects of death, injuries, property damage, and other losses. Historical background. The responsibility for the design of a safe plant operated in a manner rests with the line management. Designers designed the plant with utmost care and tried to anticipate and make provisions for all abnormal conditions. The designers may not anticipate every abnormalities. Various checking procedures are introduced and designs are circulated to various disciplines for comment and approval. This was a checking procedure on still basis by the engineers of different disciplines. The approach may not identify all hazard because it is based on the placement piecemeal system. Later in 1960s, the Mond division of Imperial Chemical Industries developed an improved system for checking the design. The system was based on the process checking rather than the taking a separate discipline for the comprehensive sense of deviation. Each part of the process was described verbally and in writing. Distinctive phrases called guide words are applied to each element of the written description to generate hypothetical deviation to see if they could actually take place and the mechanism for their occurrences, and thereon design was examined for the consequences. The system revealed a number of faults which had escaped actions by the traditional methods. In the next advancement, the written description of process was replaced with flow sheets and the plant was divided into small parts. That is, concentrations, change in effluents and emissions, change in the proportion of mixtures, additional reaction reactors or other locations, feed change, alteration of sequence and quantities in limited process change, reaction changes, reaction with the material construction. All these things are covered in this. These are area where we have to concentrate more: the physical condition, pressure, temperature, shape and size, and effluent. HACCP study follows the sequence: define the objectives and scope, select the team, prepare for study, carry out the examination, follow up and correct the result. Objective of HACCP study: to check the design, to decide whether and where to build, to decide whether to buy an equipment, to obtain list of questions to put to a supplier, to check running instructions, to improve the safety of existing facilities, etc. The HACCP study team, the team may be composed of the following: that is, mechanical engineer, chemical engineer, person from R&D, production manager, project manager, instrument and electrical engineer, civil engineer, and the team should not be too large. Whereas whenever any team is going for design oriented work, then people should also consider maintenance engineer, because maintenance engineer will know the problem when he goes for maintenance. The design engineer at the stage of initial stage, he may not be having thorough knowledge on what kind of maintenance problem will come and how to tackle. So there should be a maintenance engineer also in the team. Various methods of HACCP studies are described here. Dow Safety Guide, HACCP studies by ICICI, Chemical Industry Safety and Health Council. These are very described studies. Then I am coming to guide words. The guide words are used in conjunction with operating parameters to qualify the intention of integrity of each part of the design and also stimulate the creative thinking to discover deviation. These guide words may be applied to process condition, activities, material, time and place. These are, it is given in the chart what are guide words. The guide words are no, more, less, as well as, and part of. Where it has to be applied, it is given here: application to put into material, application to desired activities, and further. These guide words are very useful for any HACCP studies. So when the team goes for collection data, these are the things we are given here. The amount of preparatory work depends upon the size and the complexity of the plant. The data must be sufficiently comprehensive to cover the defined area of study. Continuous plant requires minimum preparatory work as flow sheet and pipe and instrument diagram. Sufficient information for study. But in case of batch plant, the addition to drawings, it is necessary to know the sequence of operation and the activities of the operator to be represented by means of flow process chart. A list of typical data required for study is also given here. List of process material with relevant data, process description with the material, heat balance, associated process flow sheet, plan of the installation showing location of various component, P&I diagram allowing the following data needs to be prepared. The volume, pressure, temperature of the material present in the normal process condition, piping and its fitting, detail with the material, design pressure and temperature, pressure relief devices, type, set pressure, capacity, methods and location of discharge, mechanical safety system in form of interlocking, various pieces of equipment with the design pressure, temperature, maximum accepted operating pressures, construction materials, operating temperature, dimensions, corrosions, erosion allowances, the pump, compressor, and similar equipment with the design pressure and maximum accepted operating pressure, maximum expected operating pressure, temperature, delivery heads, capacities, type of seal, type of pumps and device, the process control equipment capacities, alarm system, the action upon signal. Piping diagram, drawing showing the area of classification associated with the possible source of ignition. This will be helpful for fire related firefighting. Data on utilities, example steam, cooling water, inert gas, electricity and instrument here. Description of operating instruction and procedure. The SOP also it should be covered here. Description of emergency system. This will be very critical area where in case of any emergency, how the evacuation system should be arranged. There should be a chart, evacuation chart should be placed in appropriate places, and who in case of any emergency there should be a emergency site and emergency director and all, and people should be trained for this emergency conditions, so that at the time of real emergency they can easily escape from the emergency point. A team ideally consists of 3 to 5 technical members, and groups should contain sufficient expertise to provide the necessary technical input. For new project, there should be a leader, commissioning manager, project engineer, technical, process design engineer, instrument engineer, facilities engineer, and research chemist. For existing installation, there also should be a team leader, production and or process engineer, maintenance engineer, instrument engineer, R&D chemist, and safety officer. As of methodology, it is fundamentals is given here. Study leader must explain the purpose of the plan to all the members of the team, explain the purpose of the first flow sheet or operating instruction and first vessel. The study leader select the first line or operating instruction. Technical member expresses the purpose or design intention of first line. Study leader applies first guide words to generate hypothetical deviation. Make search for all possible of deviations. Team member interpret this deviation in real terms. Study leader encourages team to seek causes and consequences. Study leader only interpret when necessary and encourage team to do the creative work. Study leader will use only diagnostic questions. Study leader checks that all interpretation for first guide word have been found. Identify these hazardous consequences. Select the line, including all pieces of equipment included in the line section. Explain line design intention. Determine the material and activity statements. Apply the first guide word to the material. Develop a meaningful deviation. Examine the possible consequences and detect hazards. wherever guide words are coming, that each and every guide word should be properly analyzed. Unless otherwise we get answer for that particular guide word, we should not move ahead for any kind of studies.
I think
Record hazard, apply first
Madam-
guide words to activity.
Madam, I can speed up the presentation.
Repeat steps 5 to 8 or mark line as having examined. Repeat to 1 to 12 for each line. This is HACCP study result. The one after study, they should prepare a chart or working sheet. The working sheet format is given in this format. This is a way one that format is covered here with examples. It is given in the paper text. Follow-up work. After completion of the study, one has to follow up work. The result of the study is separated into hazardous report and operability problems report. The identified hazards and operability problem will be ranked and sorted in accordance with the ranking criteria. Ranking helps in prioritization of resources allocation. The study is not over until follow-up is completed by the management and implement all the agreed actions. Benefit is given here. HACCP is a systematic, thorough review facilities design and operation. This helps the team members to identify operating errors which may lead to serious consequences.
So boss, I think we have to speed up. We are.
Just I will 2 slides. Sources of predictive evaluation of events leading to incidents that have never occurred. Improve the plant efficiency by discovering situation of the plant, upsets, unscheduled shutdowns, equipment damage, etc. Act as a training tool for operating personnel. Helps in improving manuals and startup procedure. Need of HACCP study is also felt because regulatory authorities are requiring evidence of a systematic search for hazard, particularly to the general public and the environment. It provides better design, safer plant, faster startup, smoother operation. Summarizing the benefits, this manufacturer is benefited due to profitability, production stop due to increased safety and safe operability, and general public due to reduced risk disaster. It is to conclude that HACCP is used as a part of quantitative risk assessment, that is QRA, or as a standalone analysis. HACCP is a more detailed review technique than HACCP. The purpose of HACCP is to investigate how the system or plant deviate from the design intent and create risk for personnel and equipment and operability of the problems. This is the very good study material we can use for any kind of work, even small garden work also this can be used. And it's from that to process safety and any reactor safety, it can be applicable. And here I conclude this. Thank you.
Thank you, Mr. Bose, for highlighting the HACCP studies. Now I think Mr. Krishnalok is online, I suppose. So then we can have the second paper, that is A08 safety system for two-seater aircraft. Mr. Krishnalok, you are online?
Yes, ma'am. Share my screen.
Yeah, please.
Kindly maintain the timing.
Maintain timing.
Because we are getting delayed.
Are you able to see my screen?
Yeah, we are able to see.
Yeah, please
I'm
go
not
ahead.
able to see. This is what happened last time on show. Can I go ahead?
Yeah, please.
Yeah, the
I
safety
think
system.
time is.
I see. Good evening to all. Next slide. The preamble. You are able to see my slides right now?
Yes, we are able to.
Yes. The preamble, regulation and equivalent level safety, design aspects, the types of parachute, the sequence of operation, various aircraft already having the safety system, summary and references. The preamble, the safety system is discussed here is of a airframe parachute system. Designing APS system is specific to an aircraft. This is a total airframe safe landing and recovery system for an aircraft. The design of APS becomes the first of its kind certified with the FAA in 1998. In 2014, the Cirrus SR-20 aircraft ballistic parachute used as a standard equipment by an aviation company. The first aim of APS is the survival of members in the aircraft, and secondly, the airframe damage prevention. So in the 2021, 104 successful parachute deployments have happened and no fatalities have occurred when parachute was deployed within the speed and the altitude parameters. The SR-20, the Cirrus aircraft, which has around 1300 kgs weight, is powered by 200 HP reciprocating engine. It has a conventional tractor configuration, then it utilizes the composite for the structure. Some unique features of SR-20 include the side stick control and ballistic recovery system based on the general aviation recovery device, certified for Cessna 150 and 150 series airplane. The Cirrus plans to offer the guard system as a standard equipment, meeting the special conditions. The special conditions for the guard prior to SR-20 were the supplementary safety devices and not a primary safety device. The guard as a primary safety device and a request from FAA to give a credit for the system by accepting as a safety device equivalent to 23.21, which is PINS. The BRS founder, Boris Popov, invented the first whole aircraft rescue parachute system in 1980s. They developed a standard CAPS equipment on Cirrus and Icon A52. The BRS standard on Icon A5 and SR-20, SR-22 are available for Vans and Ubercraft, the Glacier, Landcare, and 30 and 350 other models are either they built or retrofitted in the aircraft. The only retrofit certified are Cessna 172 and 182. The Chandrayaan-2 of ISRO headquartered in Bangalore. It has no parachute system. There is Mars lander, the Perseverance, descent and touchdown with the parachute system. So coming to the regulation part, there must be a clear and distinctive stall warning with flaps and landing gear in normal position in a straight and turning flight. The stall warning must begin at a speed exceeding the stalling speed by margin not less than 10 kilometers per hour and must continue until the stall occurs. When following the procedures finished, the stall warning must not occur during takeoff with all engines operating. Takeoff continued with one engine inoperative during approach to landing. The stall warning must begin sufficiently in advance of the stall for the stall to be averted by pilot action taken after the stall warning first occurs. For acrobatic airplane, the aircraft stall warning may be mutable, provided that it is armed automatically during takeoff and rearmed automatically in the approach configuration. The spinning, the single engine normal category airplane must recover from one turn spin or a 3 second spin, whichever takes longer, in not more than one additional turn after initiation of the first control action for recovery, or demonstrate the compliance with an optional spin resistant requirement. No control forces or characteristics encountered during the spin or recovery may adversely affect the prompt recovery. During the stall maneuver, the pitch control must be pulled back and held against the stop. Thus, using the ailerons and rudder in proper direction, it must be possible to maintain the wing level flight within 15 degrees of bank and to roll the airplane from 30-degree bank in one direction to a 30-degree bank in another direction. And to reduce the airplane speed using the pitch control at a rate approximately 2 kilometers per hour until the pitch control reaches the stop. Then the pitch control pulled back and held against the stop, apply full rudder control in a manner to promote the spin entry for a period of 7 seconds or through a 360-degree heading change. Whichever occurs first. If 360-degree heading change is reached first, it must have taken no fewer than 4 seconds. Now, coming to the acrobatic category airplane, the airplane must recover from any point in a spin up to and include 6 turns or any greater number of turns which certification is requested, and not more than 1.5 additional turns after initiation of the first control action for recovery. However, beyond 3 turns, the spin may be discontinued if spiral characteristics appear. The applicable airspeed limits and limit maneuvering load factors must not be exceeded. A flap extended configuration for which the approval is requested. The flap must not be retracted during the recovery. It must be impossible to obtain unrecoverable spins with any use of flight or engine powered control, either at the entry or during the spin. There must be no characteristic during the spin, such as excessive rate of rotation, extreme oscillatory motion that might prevent the successful recovery due to disorientation and incapacitation of the pilot. So these are given in the document and the FR 1996. So coming to the equivalent level of safety, this is again similar to underwater 23.201. In an uncontrollable downward pitching does occur, it must be possible to hold the full stick off for at least 2 seconds after the nose pitches downward and maintaining the wing levels within 15 degrees of bank. Then the stall characteristics must be unduly sensitive to side slip during the abuse stall entries, and there must be no uncontrolled tendency to spin with small deviation from coordinated flight during the stall and the recovery. The use of aileron and rudder must not require a high degree of skill or alertness. The aileron must produce correct and unreversed and effective response throughout the stall and recovery. In the following abuse control entry stall controllability demonstration, the aircraft must respond immediately and normally without unreversed use of the control and without exceeding the temporary control forces specified in the 23.143 begin the coordinated unstalled flight. So these are the further some given, like if JAA is there and FAA equivalent level safety basis. There are no complaints to JAA exception, equivalent level of safety to 23.221.
Mr. Krishna, your voice I think is feeble, but can we just highlight the important points?
Yeah, just start doing that.
The slide is having a lot of information. If you can just highlight the important points in the slide,
Yeah, I'll do that.
it will
now.
save some time.
Yes. This is the FAR agrees with the continues to promote the spin resistant continuous and effective preventing the stall accident, and they have agreed with the manufacturers will see the safety merits of the approach to preventing the stall and follow the seriously to the so that the FAA can begin to see reduction in the significant causes of the fatal accidents. So these are some warnings given in this aircraft unusual attitude which recovery not expected beyond ground. The immediate deployment of the caps is required. The minimum certified altitude loss for cap deployment from 1 ton spin is 920 feet, and activation of higher altitude provides enhanced safety margin for parachute recoveries. So here it is given that less than 200 knots and 300 feet is the requirement. We have 0 fatalities, and with this 84 caps are saved with the airframe parachute system. So coming to some design technical specifications to build or retrofit your aircraft with parachutes that makes aircraft safer. The BRS invented the whole aircraft system in 1980s. They installed it in 35,000 aircraft. These are the 2 diagrams that are given. So the weight is around 38 kgs, and the placement and luggage compartment accesses to the right side of the aircraft. The rocket parachute assemblies requires all around 20 inches. These are the basic system specifications.
Mr. Krishna, can I interrupt?
Yes,
For
ma'am.
me, your voice is very feeble. Is it like that?
Voice is feeble, is it?
No, ma'am, it's clear for all of us here.
Okay.
Yeah, please go ahead. You have very little time. Can you please speed it up?
Yeah, I'll finalize in 2-3 minutes. The construction, not just showing you the detail, the construction of the canopy and the vertical tape, radial tape, the inflated profile, the flat circular ribbon parachute here, the conical ribbon parachute, and the typical bore construction of 22 feet diameter, 20-degree conical ribbon parachute here. And then these are some of the equations that goes through in the designing the CD into S into Q is the drag, parachute drag, and the deep pressure extension is integral of the P cos theta into ds. So what are the sequence happens when they open the parachute? Opening of canopy mouth and air mass moves along canopy. Air mass reaches the crown of canopy, and then influx of air expands the crown. Expansion of crown resisted by structural tension and inertia. enlarged inlet caused by rapid filling and skirt over-expanded ground and momentum of surrounding air mass. So what happens when you pull the deployment handle, rocket fires, the chute extracted, the speed sensing slider controls the fast chute open and full parachute inflation and aircraft gradually lower to the ground. So there are some YouTube are planes safe with parachute safely, and there are no parachute on passenger planes. So these are the activation cable, and this is the place where it is located, the airplane. And then airplane parachute, the original inspiration of the whole airplane parachute on the subject was meteor collision that could have led to tragedy, but instead it led to the creation of a Cirrus airframe parachute system, the most significant safety innovation in over half a century of the general aviation. So these are some of the various aircraft already having this safety system. The milestone of 400 and 401 first lives were saved on March 2019. The pilot Cirrus aircraft engine, whole aircraft rescued over water more than 20 miles from the ground island, and neither the pilot or passenger were injured. They were picked up by a cruise ship. And secondly, the Icon A5, so having this parachute system, which is spin resistant, unexpected. When we encountered the unexpected, we have got to cover literally. And this is IPS technology, has more than 300 document lives saved, and altitude as low as few hundred feet also they can deploy. And the Lisa airplane from French ACOA is fitted with an emergency aircraft parachute system that enables the aircraft and passengers to land in safe. The ACOA amphibious aircraft that is known for its elegant design and streamlined forms and gracefully curves is unveiling a new side with personality with new designs. So coming to our own country's Nishant and recovery, it has an airframe. The recovery, we have the parachute system. So these are some details which are given. Not, in the interest of time, I'm not reading it out. I hope you know about Nishant. So coming to the two-seater aircraft, the single engine.
I think we can move to the last slide, please, because there are two more speakers waiting.
Yeah, just go through airplanes you can say, and this is my last slide. The summary is what the importance of safety system is highlighted in this presentation. The airframe parachute system already exists in some of the aircraft that we have discussed, and some of the technical details presented and location defined for the parachute safety system shows how regulatory authorities approve this safety system, and it is not an optional and it's a mandatory. The needs of the incorporate to our first in unmanned aerial vehicles that will be gives us the confidence to go ahead. And this can save many lives. There are some references and then acknowledgement, and that's it. Thank you. Any questions?
Thank you, Krishna. I think, can we go to A09, which was the third paper, experience with deterministic and probabilistic, reliability analysis, experiences with deterministic safety.
I think the author has not joined it. We can move ahead with the last one.
Okay, so then we'll go to the last paper, which is the use of simulator experience and insights in design control for new nuclear power plants. Miss, yeah, please start, but try to see that you take the time, 10 minutes time.
Yes, ma'am.
I think running late.
Yes, ma'am. Sure.
Yeah, you can start.
Good evening, everyone. Honorable Chair, I present to you this paper on use of simulator experience and insights in the design of control room for new nuclear plants. And by new nuclear plants, I mean advanced nuclear reactors, where we are heading towards generation 3 and generation 4 plants. So this would be the layout of my presentation, where I would be giving a brief about the control rooms, how they have evolved, the simulators, how they are going to contribute towards the development of newer control rooms, the development of human reliability assessment method that also is aided by the simulator, some merits and demerits of the simulator studies, conclusions, and then references. So looking at the evolution of reactors from the early times, we see that from early prototype reactors, we have gone to evolutionary reactors. And the thing which we have to note here is that we are moving towards more advanced systems and less of operator actions. This is implying that you have more digital or digitalization of systems taking into consideration, and hence people or operators who are working with these systems must be equipped with the right knowledge and must not feel any stresses because of the digitalization process. So moving to the control rooms, which are the eyes and ears of the operators, they are monitoring all the plant operations and they are taking up the maneuvering actions with the help of control rooms. And the thing which we need to consider here is about the evolving atmospheres. Starting from the early reactors, wherein you had analog systems in place, we are now moving towards more and more of hybrid analog digital systems or towards completely digital systems. This digitalization of control rooms is on one side an advantage to the operators because it is equipping them with more information on a lesser space, but it is also adding to the additional stresses, which might be because of the multiple interfaces which they have to scroll to get towards the right information. So there are some standards and documents which are available, internationally approved documents for designing of the control room, for designing of this layout, the displays, all that have been listed here. And they are provided by either IAEA, IEEE, IEC, along with other ISO agencies. Now, how this is contributing towards the human reliability analysis? Human reliability analysis is basically analyzing, identifying how humans contribute towards errors in our systems, because they are an important link in our complex systems like nuclear power plants, and they would be contributing eventually to the probabilistic risk assessment values or the risk numbers. So looking at the 3 steps we see here: task analysis, human error identification, and quantification of human error, wherein again simulations or simulators can play an important role. So this is where the simulator studies can pitch in and provide important intercepts. Now, if we are talking about human reliability assessment tool development, there are definitely methods available, and this is what is contributing towards the probabilistic safety assessment calculations. What is required here is about the validation of these methods and also whether one method can be applied to any other countries, because there are methods available and people are specifically using their own developed methods. The problem with validation and widespread use of these methods is that the data is very limited, and most of the times we are relying on expert elicitation techniques, which might vary from person to person. So a specific analysis which we did from plant specific data on a research reactor showed that we used here the ThEREP handbook, that's the technique for human error rate prediction. And we see that 55% of the errors were on the commission side, errors of commission, and 45% were where people omitted some of the procedures. And that is why the need for identification of human factors is very important. What is the operator training like, how is their working environment, the procedures, everything comes into picture, and even the human machine interface. This will all contribute towards determination of human reliability and effectively will be helped by the simulators. Here I can show you the difference between the calculations done with the help of ThEREP handbook and the plant specific values. So we took data from the logs available for a research reactor, and then we took out the probability of humans making an error. The probability of an error which is made by humans is quite low, and that is why even the differences are quite insignificant here, which we can see. But the thing is that what is to be pointed out here is that there is a non-conformity. ThEREP is a very established method, and we still see that there is difference between the plant specific values and the ThEREP calculations done. And this is what calls for identification of your own methods, identification of the performance shaping factors, which will help us develop our own methods and quantify human errors. Now, how simulators are contributing to it? So we can have simulators which like simulating the exact replica of your control rooms. This can be done in a replica mode or in a full scope mode or in a limited scope mode. And even personal computer based simulators are available, and this can be accessed through the IAEA website. The advantage here with working on simulators is that both all the normal and emergency operating scenarios can be easily identified, those which could not be encountered in normal working conditions in our power plants. This is eventually going to help us in development of our advanced reactor control rooms, because they will be more or less on the digital platforms. So here we can see a prototype of a simulator which is built. So we can have both full scale or full scope simulators depending upon the applications. Now there are some merits and demerits of going with the simulator studies. Of course, they are helping with the training and development part of operators. We can train our operators to be more equipped in the actual control rooms in emergency scenarios apart from the normal working scenarios. We also can identify safety critical scenarios because the environments are evolving, the reactors are evolving. So we need to relook at the scenarios which will be of importance in the coming times. All the dynamic and emergency scenarios, along with beyond design basis accidents, those which do not involve core meltdown, can also be analyzed with the help of simulator exercises. It will help us in conforming to our national and international procedures and help in licensing of our reactors. This is also help us understand the error causing factors, design deficiencies that are there in our reactors, and identifying the most crucial performance shaping factors which will affect while our operators are working in the control rooms. Of course, on the negative side, we do have a higher economic liability, because for every simulator that you put in, you will have to incorporate a lot of funds. And every time when you upgrade your reactor, you will also have to upgrade your simulator to make sure that they are in conformance with each other. Of course, this is also an advantage because you first upgrade your simulator, have learnings on the simulator, and then replicate on the actual control rooms. We can see casual behaviors or reluctant nature of humans while they are working in simulator environments, because they might think that they are already giving us sufficient indication. So we need not be operators, we can just be managers, or we can just look at the situations and go by what the systems are telling. But at the same side, we can have logics which are not running on safe side or not running on the correct ways. So giving us a faulty interpretation of the scenarios. Something which is of importance here is the simulator bias, both the environment, because we are working in an Unreal setup, and also because of the motivation of operators, because they realize that nothing is going to happen in the on the simulator environment, so they can have a more casual approach. So the things which I would like to conclude with my study is that, of course, simulators can help us understand or have a better understanding of our human-machine interactions and give us better modes of understanding. The control room upgradation will be benefited by use of simulators. Our operators will become more equipped with simulators and also with experience gained from simulators through an operator support systems. There are definitely reduced space requirements which are seen for advanced reactors, and there the simulators can pitch in and provide a very smooth access in moving towards the next generation control rooms. We can emphasize more on the cognitive aspects of humans, which are not very dedicatedly studied in most of the HRA methods. The second generation methods are targeting, but they are not able to we are not able to use all of those methods in all scenarios. Advanced training simulators have also proven their effectiveness and utility in better understanding the difficulties that people face, the shortcomings that are there of digitalization. And of course, this is helping us reduce the size of our real control rooms. So the operator doesn't have to run through the entire set of control room dimensions and see the state of the plant. Rather, it's a small and compact room which we have come up with. So it brings down the cost of construction, improves communication between the team, so that we are reducing the team errors. The situation awareness of operators is increasing, and we have much of the information available at a compact things. Of course, these systems have to be tested, validated, and improvised on the real-time basis. This can be again done with our simulators being updated with our plant control rooms. So we can see significant improvements taking place with our systems, and we can hope for user-friendly interfaces being designed. further reducing the manpower requirements in the control room without compromising the safety and security of our systems. So a better analysis of the operator behaviors is possible, and we can utilize the evolving technologies like the internet-based AI applications, mobile tracking devices, or some behavioral monitoring, where we can look at the eye movements, or you can look at different aspects of human behavior in stressful situations. And this can be done while an operator is going through the licensing or certification processes. So these are the references which I consulted for this paper, and I welcome any comments and suggestions. And before I close, I would like to acknowledge the contribution of scientific officers and operators at Bhabha Atomic Research Center who have helped me in compilation of this analysis. Thank you.
Okay, thank you, Ms. Archana. Can we have Shenu Ramachandran on the last paper, experiences? Is the author online?
I don't think so, madam.
So what do? Shall we cancel this paper, or because that is the last paper? I think we have covered all other papers. Huh?
Yeah. If he has not joined, we cannot do anything. We can skip it.
Yeah. So now, so that means we are coming to the end of this session. I will, okay, so now we'll not wait for the author, no?
Vijaya madam, I have
Yes.
one remark. The session chairman will have to give a brief report, and that will include who has missed out on presentation.
Yeah, sure.
And maybe a sort of a ranking to each one of the paper. It could be arbitrary, but at least we should know among the 5, 6 where they stand in terms of, So, so this will be required because we are planning, and of course this will be one factor. Best paper awards. So this input will be utilized from chairman's judgment. Will be one of the input in that one.
Okay.
Yeah. So you need not do now. You can even go home and you can send it to one of the.
Yeah, sure. I will send it to Senthil.
Yeah, you can do that. Thank you, madam.
Maybe by tomorrow I will send it to Senthil.
Yeah, thank you, madam. Since I am available here in this room and I am able to see Vijaya madam after a long time.
Nice to see you also.
Thank you so much, because earlier I was meeting you in ARB and all that, but now that has become there. So thank you so much, madam, and it was a pleasure seeing you as in chair actually as a session. Thank you very much.
Yeah. So do we open this discussion for some question answers, or we conclude it over here? I think some time was allotted for question answers. Probably we have eaten away that time, but should we allow 1 or 2 questions?
Probably 1 or 2.
Yeah, depending on what is your time.
No, we have exceeded the time, but we can allow 1 question to just make the session complete.
Yeah, if anyone has some question, we can just take up. I'm not seeing any hands up.
I think you can thank author, because
yeah, so I think we'll conclude. So I will just thank the authors of this session. First, anyway, since even though we couldn't hear from regarding the experiences of this one, that was an important paper. Shenu Ramachandran and experience with deterministic analysis and reliability assessment of one paper from TC Tata Consulting Engineers, I think. So I'll just briefly say they were going to present a paper on how the deterministic safety margin assessment is used for generating the feasibility of the civil structures for NPPs. That is a topic which is of all interest in this period when all extreme events are more than what are expected is happening. So probably we can read it from the proceedings. Then that was just one line of that paper which we couldn't hear. Then we had a good paper on probabilistic analysis of sustainable concrete, where he just explained how the probabilistic studies can be used to estimate the mean fracture energy of fly ash designs. So thank you, Mr. Balaji Rao and his team, and Mr. Jagan Mohan, who I think he presented the paper, for presentation and highlighting the major results of the studies. And we had a paper on the hazard and operability study, which was also explained how hazard and HACCP are used in at the early stage of design and later on. So thank you, Mr. Bose, for that paper on HACCP studies. And we had a paper on from CSIR safety system for two-seater aircraft by Krishna Lok. Thank you, Mr. Krishna, for that interesting paper on how the two-seater aircraft safety systems are being operated. And last, we had use of simulator experiences in the design of control room. Ms. Archana Yadav, that was also a good study on how the simulators can be used for improvement or rather better control room design as well as training operators. You had an interesting slide on that comparison of TERP with, but here I would like to ask you one question, since nobody has asked. What was your outcome or what was your experience? How the TERP and actual plant specific experience, how do they compare the results? Are we at par, or there is a wide difference in the human error probabilities?
No, ma'am, the difference is not very significant, as I showed in the slides as well. The human error probabilities are already very low, and the differences also are very less. The thing is, we were not able to identify the exact scenarios. Sometimes, I mean, they are given a broad range of scenarios, but we were not able to identify what exactly the problem is with according to the THERP database. So some more elaboration would be required so that we can cover a wide range of errors that humans do.
Okay, thank you. So anyway, as usual, this probabilistic are very data intensive. Probably we'll need a lot of data for that. So thank you everyone, and I think we close the session here. Over to Senthil.
Thank you, madam, for conducting the session. We are exceeded the time limit now, and maybe all the participants can stay in the same room so that the keynote lecture can start. I request Dr. Balaji Rao to give an introduction about the keynote speaker.
Yes, I think the keynote speaker is there. Very good evening to all of you. It's a great pleasure to introduce Professor Bernard Rolfe. Professor Bernard Rolfe, I'm very sorry, it became a bit late. Kindly excuse us, and that's why it was about 10 minutes late. I would give now the introduction of the keynote speaker, Professor Bernard Rolfe. Bernard Rolfe is currently a professor of advanced manufacturing in the School of Engineering at Deakin University. 1 minute, I'll just, okay. Deakin University, he completed a combined economics and engineering degree with honors in 1995 from the Australian National University before embarking on a career in business and technology consulting with Anderson Consulting. He returned to ANU, which is Australian National University, to complete a PhD in advanced manufacturing at ANU in 2002. He joined Deakin as lecturer in 2005, and his research group has spent the past 2 decades working on the use of advanced metals in sheet forming, primarily for automotive sector. Bernard was the team leader for lightweighting at Australian Automotive Cooperative Research Centre between 2014 to 2017. And he is currently the chair of the Academic Advisory Board for the International Federation of Societies for Automotive Engineering. His current research focus is on the design and forming of lightweight structures. He is also investigating design techniques for production and repairing of parts using additive manufacturing. Bernard has received 4 Vice Chancellor Awards, and he has been part of over 15 successful nationally competitive large research grants, totaling over 25 million Australian dollars in the form of awards. I now request Professor Bernard Rose to deliver the keynote lecture.
Thank you, and thank you for inviting me. Can everyone hear me?
Yes. Yes,
good, fantastic. I come from manufacturing, so I'm going to talk to you about from that perspective. I guess from a reliability and safety, I'm looking probably more like a causal analysis. Look, I'm going to talk to you about variability and defects. We do a lot of work with industry, and so this is where I'm coming from. But first of all, I should acknowledge a lot of people who've helped out on all these projects. There's many of them, and I have to primarily single out Professor Peter Hodgson, who's helped mentor me along this way, and he's had a lot to do with India as well. I have a lot of industry partners, which includes Ford Motor Company, which has been a long-time partner of Deakin. We're situated in the same city of Geelong in Australia. But just to take you through this sort of causal analysis of failure, I'm going to talk to you about the fundamentals of bending, because it's really important for metal forming. Now with bending, we have a sheet and we bend that sheet. And as we bend that sheet, it'll have a neutral axis, which means that that axis is not stretched and it's not compressed. But as if we move to the outside of the sheet, it'll stretch because it's going a bit further, and the inside of the sheet is actually compressed. So when we bend, we get stretching on the outside and we get compression on the inside. Usually it's a linear type of strain, and it leads to, if we go to a plastic bend, if we bend quite far, then we have a nonlinear stress response. So what I'm showing you to you here is most of the things that I'm going to show you has to do with bending. Now, as we get stronger and stronger materials, so we could start off with a DP means dual phase 300. So that's probably quite an old sort of just above it's quite above a mild steel, but it was a bit above what used to be the strongest steels in around the 1980s. Now, as we go further and further up into strength, we've got these magnesitic steels, which are about 1 gigapascal. So about 1400 there's UTS as an ultimate tensile strength. They're quite strong. The only problem with that is they don't bend that well. So the bendability increases with or decreases with strength. Now, the thing about when we form our parts is that we're not only just doing bending, but we're doing bending and tension. So we're stretching the sheet over the die, which means that we're bending and putting it under stretch at the same time. What that means is that instead of our pure bending as we had before, where we've got tension on the outside and we've got compression on the inside, we actually pull the sheet so that we have tension on the outside, and then we have a small amount of tension, or maybe even no tension on the inside. What that means is that our stress state changes. And it changes from being, a large amount of tension on the outside, a large amount of stress on the positive tensile stress on the outside, and a large amount of compressive stress on the inside, to being sort of quite a bit of stress on the outside, tensile stress on the outside, and less tensile stress on the inside. So this will become a bit important bit later on, but this is just taking you through the basics. The great thing about I guess well, the interesting thing about bending is that once we load our material, then we have a residual stress, or we have elastic stress that we release when we unload. And with pure bending, we can see that our large amount of tension on the outside actually becomes a small amount of compression on the outside when we unload, and the large amount of compression on the inside becomes a small amount of tension on the inside. So we get that sort of reversal when we release, and that release is called spring back, and means we move out of shape. Now, the interesting thing is when we have bending and tension, because we no longer have that large amount of difference between the outside, which has got tensile, and the inside, which is compression, we actually have a smaller amount of, I guess, reverse bend. We have a smaller amount of spring back. So one of the ways we can reduce the amount of change in the shape when we take our tooling away is to actually put more tension into the sheet. Now, that's a great thing. We can do what's known as pull out the spring back. Because we put in more tension, we can reduce the amount of I guess bending in our sheet, which gets released. But if we put too much tension into our sheet, then we get failure, and because we'll tear our sheet. So there's this fine balance between putting too much tension in and not enough tension, and getting a large amount of spring back and getting change in shape. So if we look at our sheet, and we've got it bend under a moment, and then we release that moment, you can see that it's causing that spring back, that release, that change in angle. So that angle, that change in angle, that spring back, it's related to the yield. So how strong our material is. It's related to the Young's modulus, so how stiff the material is. It's related to the size of the bend, and it's related to the bend severity. So as the bend severity decreases, we get increase in spring back. As the elastic modulus decreases, then we get an increase in spring back. And as the yield stress increases, we get an increase in spring back. So that means that if we have a steel and we replace that steel in lightweighting with an aluminium, or steel is around 210 gigapascals, Young's modulus. Aluminium is about 70. We have a smaller elastic modulus, we get an increase in spring back. So what you find is, say, like with Ford, it went from a steel body to an aluminium body. It had to reset how it did things, because aluminium has a lot more spring back than steel. Of course, if we have higher yield, as we go to higher strength steels, we get more spring back. Now, the interesting thing about bending and unbending is that as the sheet goes into the radius, it bends, and as it's coming out, it has to unbend. So when it's bending, it's getting curvature, and as it's unbending, it's losing curvature. And what this means is that the sheet actually loses contact with the tooling after around 45 degrees. That's because it's starting to unbend, and it has to actually lose its curvature, and as it's trying to straighten as it goes into the what we call the sidewall. You can also see that we go from a tension. So we were bending. Remember with bending, we have tension on the outside and we have compression on the inside. But when we get to about 45 degrees, we start to change. We start to move. Because we're unbending, we're putting more compression on the outside and we're putting tension on the inside. And you can see there's a stress reversal when we do that. So I guess I should explain why we're doing all these things. And that's because we want to develop, sustainable vehicles for the 21st century. And there's a huge middle class of people appearing when we need these low cost sustainable vehicles. And as you can see, say with Delhi's air pollution, we need to be able to find solutions to that. And that is providing or finding sustainable, cheap electric vehicles. Which means that we need to have manufacturing solutions which provide robust and cheaper solutions. And I guess to see one of the problems that we have with this, if you start off with the 1974 VW Golf, its weight, well, I'm going to ask what's the weight of this vehicle, but it's more of a rhetorical question. But think about what that weight is. And then we go to a 2004 Golf. It's more modern. It's got a more powerful engine, but it's using much higher strength steel. What's the weight of this vehicle? And what we find is that we've gone from 1974 to 2004, and the weight of the vehicle is doubled, or almost doubled. And that's because even though we've put in these higher strength materials, the safety's gone up, the comfort has gone up, the driving performance has gone up, the roominess has gone up, etc. So a lot of weight of vehicles went up, I guess, throughout the 80s and 90s and into the 2000s. And now we're trying to find ways to decrease that to get better range for electric vehicles, to reduce emissions on the internal combustion engines. What that means is that if we split up or we look at where the energy is going, powertrain is taking most of it. But if we have lightweight design and start looking at the body structure, about 15% is coming from the body structure itself. The body structure is accounting for about 40% of the total weight, and usually the body structure itself drives most of the weight in the automotive structure. So there's real opportunities in terms of looking at lightweighting through new designs and also new materials, and looking at manufacturing processes. But given this conference is more about safety and reliability, I wanted to look at more at how we have problems within new materials, and how we can look at ways for causal analysis to understand where the problems come from. So we call this the banana curve because it's in the shape of a banana. But we have the highest strength steels down at the bottom here. They have very high strength, and we have the low strength steels down here, and they have very high elongation. Ideally, we want something out here where we've got high strength and high elongation. High elongation means that we can form any sort of shape we want. High strength means that we can resist intrusion during crashes. And if we look at where body structures are going, the strong cage of the structure is going to ultra high strength steels, and the skin panels, the outer panels, are going to aluminium because they're much lighter, and we don't need the strength. We need the strength in the main crash cage. So when we actually form ultra high strength steels or advanced high strength steels, we're increasing the yield, we're increasing the strength, and that increases the spring back, and that's a problem. Now, when we look at, and this is where the causal analysis comes in, And when we look at stamping of advanced high strength steels, there are two types of advanced high strength steels that we were looking at. This is a while ago, and one's called DP. It's a dual phase. It means it has two phases. It has a martensite and a ferrite phase. Martensite being really hard, ferrite being soft. And one of these curves, a couple of these curves are dual phase, and a trip steel. So a trip steel means it's transformation induced plasticity. So when we form that steel, actually, because we're forming that steel, it transforms its retained austenite phase into a hard martensitic phase. So as we form it, it becomes stronger and stronger. So it's probably this orange curve here. It's got very high work hardening. And what our industry stampers would tell us is that trip steels were impossible to stamp, and the dual phase was okay. It had high spring back, but they could account for that. And so when we looked at it, the materials themselves, when you look over here, that it's very hard to tell what's a trip steel and what's a dual phase steel. So we couldn't understand why was there a difference. And so this is where our sort of causal analysis came in. So after a lot of discussion with the stampers, what it came down to, the problem was that the trip steels were dimensionally unstable. And what that means is that if a steel comes in and it has higher spring back, then that's okay to an extent. They can then readjust all their nominal values and then change their assembly so that their welding guns can pull the steels together. But if it's dimensionally unstable, that means that as they're stamping through the coil, the actual nominal chain and the nominal data point will actually change so that they can't put the assemblies together. And this is what the stampers hated. They hated that dimensional instability. So what they were telling us was that trip was unstable, but dual phase was stable. So why was this? Was this due to the stamping process, or was it due to the material? And so this is what sent us on this causal discovery. So when we look at the dual phase, this is dual phase DP980, and then we've got a trip steel a trip 800. You can see that there's not a huge difference between those materials. One of the things you do notice is though that the dual phase tends to go strengthen quickly early, and then it flattens. Whereas the trip steel, it's always, every time it's being formed, it goes stronger and stronger. That's the main difference. So what we looked at then was, because we could see that the UTS was very consistent. So what was it about these two materials that the trip steel was giving us problems and the dual phase wasn't? So we looked at the variability of the coil. So we did an in-coil variation test. We started to look at the probabilities there, started to look at where the averages were there for the yield, for the dual phase and for the trip, and also for the UTS, so the ultimate tensile strength. So where does it get to before it starts to fail? And we could developed our probability maps and probability distributions based on that. And as you know, a robust region is where we have large amount of input, gives us a small amount of output, but a sensitive region is where we have a large amount of input, and that gives us a large amount of output. So I just give you a quote just because we need to set some things up. Before, I guess, Donald Trump, we had Donald Rumsfeld in American politics, and he said once, "As we know, there are no knowns. That is, that we know there are things that we know we know. There are also we also know that there are known unknowns. That is, that we know that there are some things we don't know. but there are also the unknown unknowns, and the ones we don't know is the latter category that tend to be the difficult ones. So what we don't know is the real sort of problem. But what we did is we used a stochastic simulation to look at what was happening with our dual phase and our trip steels. We used something called autoform sigma, where you could take your probability distributions, put it through the stamping process, and see what comes out. So it's essentially like a Monte Carlo approach. But the thing is that we have to assume that our unknown noise, so our unknown unknowns, don't have any effect. So we're assuming a big thing because our unknown unknowns, the things we don't know, aren't having any effect. But we did this, so we put our probability distributions in and had an output response. They gave us some response windows for looking at our process of stamping parts. And they gave us like a window in strain and a window in stress. So we sort of looked at strain being our input, how much we're trying to deform our part, and the stress being the output. And you can see with bending under tension, that's what we're doing when we're creating these parts. You know, we're pulling things with our tension, and then there's a release. And what we found was that there's what we call the minimum plastic modulus. So what's the minimum slope of our hardening curve, and what's the maximum of our hardening curve? And when we start to look at that, that gave us some insight into why the dual phase was giving us some problems. So we then start to look at how does variability change as we changed our parameters. We found that as we increased our sheet tension, that we could decrease some of our variability. The problem was that once we increased our sheet tension, we get to closer to failure. So finding that balance was a key thing which we could do through this analysis. But in the causality analysis between the dual phase and the trip steel, what we found was that the trip steel had much higher variability in its essentially its minimum plastic modulus and its maximum plastic modulus versus the dual phase. So where our strain was occurring, so the strain we're putting into the part, our dual phase was flatter in terms of its work hardening. So its minimum plastic modulus and its maximum plastic modulus was much smaller than the trip steel, which kept on hardening as we put strain into the part. And by having that less difference, the dual phase was much more stable than the trip steel. And this was the reason why the stampers loved the dual phase, which is a high strength steel, as opposed to the trip steel. And you'll find if you go to any sort of automotive place now, they'll probably stamp a lot of dual phase steel, but they won't stamp any trip steel at all. And that's because they don't get the stability. So we'd solved our mystery here. We used our probability analysis. We used our sort of knowledge of materials and came up with why where the variation was coming from, and that was because the trip steel, the material, was more unstable in that in that plastic modular sense. And so I'll just take us through another causality analysis we did looking at bending. We've got one of the largest roll forming groups in the world. We're very interested in bending. We're very interested in roll forming. Roll forming is where we have a number of stands, as you can see. Each stand bends the sheet just a little bit further, and we can create quite complex cross sections by having a lot of stands bending the sheet at each station. Now, it's an actual incremental process because we're incrementally, as you can see here, we're on the top right-hand corner, we're incrementally bending the sheet to the shape that we want. And that incremental bending does allow us to have a more formability with materials than what you get if you just did a straight single bend. Now, so our industry partner had 2 different steels, and he's saying, look, I get very different springback results when I use one steel. I can't remember if it was a German steel or a Japanese steel, to the other steel. Why is that? And so it's another causality thing. We've got 2 materials. They look very similar. We looked at the chemistry. They look pretty much the same. They had the same pretty much tensile results. Why do they show differences? So even the microstructure looked the same. So then we said, well, if all those things are the same, maybe it's something to do with the processing of the material itself. So we went back to basics, and one of the things that they do in creating the sheet is what we call like a skin pass or a final reduction. They usually put in about a 1% skin pass just to make sure that the surface properties are pretty good, and also to maybe take out any sort of aging effects if you have an aged type steel. And what we found is that if you skin pass your sheet just slightly differently, so if you do 2 0.5% to get you to the full 1%, it'll actually give you a different residual stress profile than you do if you just do the full 1% in just one hit. So we then said, well, why don't we see that if we just do tensile tests? Now with tensile tests, they just average everything across the through thickness of the sheet. So by doing that, because you're averaging, you miss that residual stress profile because it just gets pulled out. But if you do bending tests, so we did bending tests to find out the yield, then we found there was a big difference between a 1% and a sheet that had skin pass with a single 1% reduction as to one that had a 2-step 1% skin pass. Why that is that when we do bending, remember we put lots of strain on the outside and the inside. Now, if we have residual stress profile, which is very different on the outside and the inside, then that really affects our bending results. And so by doing bending, and our bending tests and this causality analysis, we could see that there's a difference between the two materials. One was skin pass with 1 pass, and the other was skin pass with several passes, and that was the main finding. So I guess on our road to trying to get low-cost sustainable vehicles, to find simple manufacturing solutions, we've used our probability and causality analysis to understand bending, understand why materials are not working or are working for us in a manufacturing environment. So hopefully we can get to a low-cost sustainable vehicle. We've got our own designs. Hopefully it will be uptaken, looking at low-cost sustainable vehicles. But hopefully I've taken you through some adventures that we've had with bending, and shown how we've used, or we looked at variability and defects, and using sort of a causality analysis and probability to understand problems that we've faced in manufacturing. So with that, I'm happy to take any questions if there are any from the audience. Thanks.
Can I ask one question?
Yes.
Very, very nice presentation. In-depth analysis of variability on defects and due to bending. Impressive. Thank you very much, Professor Rolf. I have one question, which we face in industry.
Yes.
These pipes are bent, you know, especially carbon steel. I would take the example, carbon steel pipes.
Yep.
And then at the bend location, you have this thickness reduction, and this is of the order of, let's say, if it is a 250 mm normal diameter pipe, then you have around 1 or 1.5 mm thickness reduction compared to the unstressed portion, you know. And how you know that? Because when pipe corrodes over a period of time, let's say 20 years, 30 years, the corrosion eats away this location more, and you tend to have some sort of leakages location over here.
Yep.
So in industry, my question is there any technology or any development going on to have the uniform thickness all across the pipe section, especially the bend pipe section, you know, because this creates a problem over a period of time, and it requires complete revamping of the lines, and, you know, because you take one section, you take all the section. Thank you very much. Can you please throw some light on this?
So with pipe bending, you have you can get a lot of problems. Again, it's a bending, so you're going to have stretching in the outside and compression on the inside, but you now have a pipe instead of a sheet. Now, another issue you face, which you don't face with the sheet, is that pipe will actually become unstable if you try and put it under too much load, and it'll actually it will buckle or wrinkle. So to keep the shape of the tube, they actually put mandrels in to help retain that shape and to make sure that you form evenly to try and keep the thickness the same. And then I guess to get around that, what we've been looking at, and I think a lot of people have been looking at, is how you can tailor the material so when that you bend, you allow it to bend more in certain sections than in other sections, and you can drive that by tailoring the material of the tube as you put the bend through. The other issue with corrosion, I guess, will be the residual stress you put in or leave in the tube as you go through the bend. Some of that you cannot help because you are deforming the tube, so it will have some residual effect. But what you try to do with the mandrel is to try and get a very even deformation around the tube, around the bend. I don't know if I've answered your question, but that's a lot about pipe forming.
Yeah, I think it is a very interesting presentation, Bernie, and I really enjoyed as a mechanical materials processing person. Now, I think in real life, we do have these problems, like quite often my automotive exhaust pipe will kind of rupture out exactly at the bends. for two
Yes.
reasons. When they kind of bend it, your wall thickness gets thinned down, and then there is, the residual stress. That's why it creates the, recipe for early corrosion to take place over there. But recently, when I was trying this with one of the mechanics, what he did was, after he heated the pipe to get the bend radius, he also started a little bit of, tapping with the hammer. So it's more like introducing a compressive residual stress onto the
Yes.
regions which are likely to have a tensile residual stress. And he said that this is going to last a little better than the previous version. So maybe, there are these solutions, but I think I also think that one can use the gels as the fluid medium inside, and then you can try to bend. In which case, perhaps this wrinkling as well as the buckling at the edges will be avoided, especially on the inner side. And
Yes.
yeah, some of those techniques are available. But coming back to your question, like you were saying that when you keep the strain as a reference or stress as a reference, you got two different envelopes on the residual modulus or something like that.
Yes. So
Okay.
the strain was more of an input. That's the deformation we're putting in, the stress being the output. That's what's
Right. I was just wondering
realized.
whether this is like a typical, displacement controlled, elastic plastic scenario, or the stress controlled elastic plastic scenario. Very often in deformation, we have these two situations, right? Is there a parallel to that?
It's very much a strain control, as in, because you know what shape you are going to put the material into. It's going to spring back out of that shape, but you have very little control over what stress you're going to get, because that's whatever the material does. Yeah. So, and that's what we're looking at. You're forming that shape, but
yeah,
what's the material how's the material going to behave to that? So
good.
That was the interesting
I think
thing.
it's kind of past midnight, so I don't want you to kind of.
Yeah, it's 12:30.
So let's see if there are any questions from the audience. Otherwise, I think you gave a completely different flavor to this conference, with the more of mechanical and materials processing variables that affect this.
Yes,
so I think we will just hand it over to the session chair, Dr. Balaji.
Okay. Thank you.
Okay, thank you very much, Professor Rolfe. It was a very illuminating lecture. It was very useful and very, you brought out the importance of consideration of uncertainties in the form of upper and lower bounds. And it is very illuminating. I'm sure that it is very useful for this community. Thank you very much once again. As Professor Raghuprakash said, I think it is already midnight, past midnight. Thank you for all that. Thank you very much. Very kind of you for giving this keynote lecture. Thank you very much.
Thank you.
Thank you, everyone.
I think we can hand it over to Professor Sudhakar. Hello? Hello?
I'm here, sir.
Madam, shall we?
Yes, sir. So next we will have a technical presentation session.
Correct, madam.
So there is a breakout room named a technical session 4. So I kindly request the participants to move on to the breakout room named a technical session 4. So based on your schedule. I also request Manoharan sir and Vaishnavi madam to kindly move to the breakout room.
In the current room, I think the authors of technical session 3 can remain in the same room.
Yes.
A54, A51, A49, A47. These are the abstract numbers and the authors of these abstracts can remain in the same room.
Senthilji, just to
Yeah.
confirm whether my voice is audible to you.
Yeah, you are. You're audible.
And just let me check my video also.
Yeah, you are clear.
Okay, fine, great.
So, madam, can we start this technical session 3 here? And
yes, sir. Please, sir.
Yeah.
Again.
Good evening. This is the start of the technical session 3, probabilistic safety assessment, part 2. And this will be chaired by Dr. R.B. Solanki of Atomic Energy Regulatory Board, Bombay. So I'll give a brief introduction about the chairperson for this technical session. Dr. R.B. Solanki joined AERB after completion of his MTech in Energy Systems at IIT Bombay in the year 2000. He has been involved in review and assessment of PSA and conducted more than 100 meetings of AERB PSA Review Committee. He was deputed to United States Nuclear Regulatory Commission as foreign assignee during June 2005 to July 2007. He was instrumental in development of PSA-related regulatory safety documents in AERB. He is also associated with the safety review and assessment of Indian nuclear power plants of all designs such as pressurized heavy water reactors, light water reactors, and fast reactors, which is under construction. Dr. Solanki represented India in many international forums. He is conferred with PhD degree from IIT Bombay in the year 2019 in the field of passive system reliability assessment and its integration with PSA. Dr. Solanki is currently involved in developing regulatory strategies for regulation of advanced reactors and developing regulatory requirements and guidance for nuclear power plants, entering into the LTO regime, long-term operation, and subsequently towards decommissioning. So with this introduction, I request R.B. Solanki to take over and chair the session. Over to Dr. Solanki.
Yeah, so thank you so much, Dr. Senthil Kumar, for your kind words. So with this, we will begin this session in which we have 5 technical papers. And as all of the authors knows that this is a kind of a schedule that is being prepared. So accordingly, you are getting a 10 minutes each for your presentation. And at the end of all 5 presentation, I think we have been allocated around 20 minutes for question answer. So I would request all the audience to note down their questions and the speaker name. So it will be easier for us to identify and have a fruitful discussion at this end of the session. So with this brief introduction, now I will invite Dr. Senthil Kumar to present the first paper, which is on the development of multi-unit probabilistic safety analysis. And Dr. Senthil Kumar, please.
Thank you. I'll just share the screen. I think your screen is shared.
Just let me switch off the screen, sir. Okay.
Yeah, is it visible, my screen?
Yeah, it's visible now, Senthil Kumar.
Yeah, I'll. Yeah, my talk is on the methodology for multi-unit probabilistic safety assessment. I work with the Atomic Energy Regulatory Board and placed at Southern Regional Regulatory Center, Chennai. So before I start, I would like to tell the importance of multi-unit PSA because there are participants from the academia here and industry, other industries, non-DA units. So the distribution of operating nuclear power plant worldwide and in India is as follows. On the left side, you can see the latest database of released with International Atomic Energy Agency 2021, which indicates that there are totally 446 operating reactors worldwide, and out of which 90% of the reactors, around 401 reactors, are situated at a multi-unit site. And in India, we have all the nuclear power plants, 22 power plants at multi-unit sites, which are indicated here. 2 reactors are at 4 sites have 2 reactors, and so on. 4 reactors are at 2 sites, TAPS and KGS, and 6 reactors at RAP site. So the importance of multi-unit PSA is, so for the simultaneous failure of systems and components at multiple nuclear power plants in a site were considered very rare, and it was not given enough importance earlier in PSA risk assessment studies. But after the Fukushima accidents, the necessity of multi-unit safety assessment and the need to develop safety goals, procedures, and guidelines to achieve and maintain the safety goal was felt to protect the public and the environment. Even earlier, there was studies going on, but the importance was less. But after the Fukushima accidents, it got more importance. So to give a brief introduction about how a multi-unit site in general looks like, on the left, you see the single unit site. I've given a typical PHWR site where we have the supporting support systems for the operation of nuclear power plant. I would like to brief for the other non-DE persons that why a DG is required here. During a loss of offsite power, there are safety systems which require the backup power supply, and that is the reason we provide diesel generators. And we also have normally redundancy provided for the diesel generators and a backup for that. And other utilities like switchyard, fire water injection, compressed gas station, seawater pumpers, etc. are also the support systems for the nuclear power plant. In a twin unit site, normally we have the resources shared between the units, and here comes the issue of the importance of multi-unit. So there are some systems which are shared between the 2 units, and that is the whole purpose of having multiple reactors at a site. Some of the examples I have shown here, which are the systems that are shared between the units. And in general, we follow a twin unit sharing system. That is 2 units at a site will share the resources together, and it goes on. Like 4 unit site, 2 pairs of units will share the resources in general. So the risk metrics, what we follow is for a single unit site, we single unit PSA, we have the traditional risk metrics of core damage frequency and large early release frequency, which are expressed in the units of events per reactor year and are associated with each reactor on the site. But when it comes to multi-unit site, we need to develop a risk metric depending on the type of facilities or the type of radioactive sources present at a site, such as reactor units where the core damage is an issue, spent fuel storage units, etc. So the site for the first issue in multi-unit PSA is to very clearly define what we mean by the site risk metric. The site CDF and site LRF needs better definition and characterization when applied to multi-unit sites. And there are experts internationally developing a common site safety goal in connection with risk-informed regulation. While it is believed that safety goals are the reflection and interpretation of PSA results, it is also understood that the adherence only to the probabilistic criteria is not realistic because of the inherent uncertainties involved in the in various steps in probabilistic analysis. And since there is no prescribed safety goal for a multi-unit site as of now, the target specified for a single NPP is considered applicable for a multi-unit site also. And this is justified because we are talking about the safety of public and environment, irrespective of the number of sites at units at a site. For risk-informed decision making, the risk aggregation, which is an important aspect for a multi-unit or a multi-facility site, needs to be carried out in an integrated manner where we have to take into account the human, organizational, and technology factors altogether. So with this background, Atomic Energy Regulatory Board started the initiative to develop and demonstrate a multi-unit PSA methodology and draw insights from applying this method on the benchmark site. And this we have as we know, the PSA has 3 levels, and we have concentrated in developing a methodology for level 1 PSA, where it restricts only to the system level analysis. That is core damage frequency. It doesn't go into the level 2 and 3. And this will also help us to build expertise for independent review and assessment from the regulatory point of view, as and when the utility submits the multi-unit PSA risk assessment. So the methodology we adopted was first to identify the site-specific hazards and the multi-unit initiators. And then for these multi-unit initiators, we have to develop a multi-unit event tree similar to the single unit approach, but specific emphasis has to be given for the shared or the interaction of the systems that are serving 2 units at a site. And build fault trees by modeling inter and intra-unit CCF common cause failures, human reliability analysis, and shared resources, and the inter-unit interactions. And finally, perform the safety analysis and estimate what is the multi-unit core damage frequency. The deliverables expected from this study are firstly to identify the risk contributors and the structure system components that are important in multi-unit sites. And then what is the contribution of external and internal hazards to the site core damage, and also to provide severe accident scenarios for level 2 PSA at a multi-unit site. And the complexities that are postulated was modeling becomes extremely difficult, and the number of accident sequence increases exponentially when the number of units at a site is more. And also another complexity is to consider the different operational modes of the reactors at a site. So whether we have to consider the full power operation, low power, and all the combinations of these operating modes is a complex task. And when a multi-unit site has non-reactor facilities, again, the risk aggregation becomes complex. So with this background, we had developed a multi-unit PSA framework in around 2015, where we had an advantage of level 1 PSA completed by the utility for all the nuclear power plants in India. And that gave us the starting point. With that as a background, we try to identify the initiating events for a multi-unit site, that is multi-unit initiating events based on the operating history, the expert judgment, and site-specific hazards. And then for the multi-unit initiating events, we developed the event trees, where when we are developing the functional events for the event trees, we took into account the interactions and the common systems that could serve common functional events that could serve multiple units, and develop fault trees to pertain to single unit separately, and also the modeling of the shared system within the fault tree, taking into account the common cause analysis, which I said earlier, between the units and within the units. And finally, the modeling and including HRA was a bit difficult, though we have not done a comprehensive study. We try to attempt this human resources modeling in the multi-unit. And then finally, the system analysis to quantify all the multi-unit accident sequences, and where for the external events, we have to do the hazard analysis and incorporate. And finally, we calculate the single unit CTF and multi-unit CTF and have a comparison of this. So to carry out this analysis, the basic method we followed is for the internal and external hazards, we try to identify the multi-unit initiating events under 2 different categories. One is those hazards that will affect multiple units, definitely. Like for example, seismic event or external floods or tsunami or external fire, that will definitely affect all the units when this hazard takes place. And another category is the conditional hazards, where only under a certain condition it will have an impact on the other unit when it is adjacently situated. So these 2 categories we develop for external and internal hazards, and try to identify what are the initiating events under each category of these hazard events. So with this, while developing the fault trees and event trees, all the multi-unit factors were addressed in the modeling itself. Though it is complex, we try to model to the large extent and fit in the form of fault trees. And finally, after the accident sequences are evaluated, we try to find out the site core damage frequency, which is nothing but the 3 summation of CDF. That is summation of I to 1 to number of units present at a site, and J runs from the 1 to 5, the category of hazards: definite external hazard, conditional external hazard, definite internal, conditional external internal hazards, and then the independent events. And K1 to M is the number of initiating events under each category. So with this, it looks like a simple summation, but while modeling itself, we take care of the multi-unit factors, and though therefore this summation is not a straight summation as it looks. And then after this methodology was developed, we try to compare it with the international scenario, where IAEA compiled the available methodology or approaches followed internationally, and they categorize three types of methods that are followed for this multi-unit PSA. First method was the event sequences, where
Dr. Sen,
yeah,
just to interrupt you, we are running short of time, so I would request you to.
Yeah. So three methods were done. One is the event sequence method, where the only the unsafe sequences of the first unit was progressed further for the second unit. But this type of modeling had a difficulty of not identifying the single core damages. It considers only the double core damage frequency. And the second type of methodology that was followed was the master event tree approach, where the initiating events for each unit was developed in the usual manner, and the core damage accident sequences were developed in the form of a fault tree, and then the multi-unit initiating events and the corresponding initiating events were plugged in there. And the third approach was followed by Carey. It is an entirely fault tree kind of approach, where the site core damage is due to a particular initiating event is considered as a top event, and then the same initiating event, how it can occur in single units, were formed in the form of a fault tree. And similar initiating events for the other events were also followed. So in all these three comparisons, our method was very comprehensive, though it is complex to model when the number of units increases. These are some of the points which I already highlighted, which were difficult to manage, but it was important from the multi-unit PSA point of view, like modeling of shared system, treatment of dependencies, common cause failures, the mission times to be used, and also the combining the risk contribution from different hazards. Yeah, we tried to implement this on a 20-unit site in coordination with the NPCL, and what we found out was the two simultaneous core damages was contributing about 4% to the site core damage, and then the internal events is contributing more than the external events. This is this general belief of external hazards dominating multi-unit risk may not be always true. That is our conclusion based on our case study, but it depends on the site-specific characteristics and the design configuration of the plant. So these are the insights that are obtained from this case study and implementation of this methodology. The scope of the multi-unit PSA needs to be very clearly defined, and it is important to clearly define the operating states to be addressed when there are multiple reactor facilities, and identification of potential initiating events that can affect more than one unit simultaneously. I think the screen is. More than one unit simultaneously, the complexity of combined inventory increases progressively as more units are taken into account. As in most of the cases, as in most of the cases, single unit PSA is completed prior to multi-unit PSA, which gives a clear understanding whether to include or exclude a single unit accident sequence in the risk matrix. And also a systematic approach is required to limit the number of multi-unit initiating events, as it can exceed when the number of units to be considered are very high. And sensitivity analysis is also mandatory, as we do for the PSA. And this is my last slide. The appropriate screening process is required to limit the proliferation of accident sequences. And the uncertainties with respect to external hazards is generally large, and especially from seismic risk, it is very uncertain. And it is important to understand and model the dependencies among multiple units. Use of appropriate models for the CCF inter and intra unit is important. And the performance safety factors in HRA is in the multi-unit context has to be addressed properly. And of course, the combination of different operational modes, which I said earlier, also have to be given importance. And finally, the safety goal and the quantitative target for a site must remain same for a multi-unit site, independent of the number of units at a site. Thank you. I think I exceeded a bit.
Yeah, so thank you, Dr. Senthil. It was very insightful work, especially when you say that, different units in a different operating mode, adds to the complexity in whatever work that you have already, taken into account. So I thank you for your presentation. And in this session, the next presentation is on, let me just see, application of probabilistic risk assessment approach in nuclear power and space sectors by Srimati Janki Devi Kompela. So I would request one of the authors of this paper can present their work.
Yes. Let me present my screen. Yes. First of all,
Yes,
am I audible?
Yes, yes, very well, loud and
Okay.
clear. So you can start your presentation.
Thank you, sir. First of all, good evening, respected chair, organizers of NCRS 2022 conference, and fellow authors and audience. I am Vignesh Anandan, working as a senior consultant at RelSafe PRA Consulting Private Limited. I would like to say that we are very happy to be associated with SRISA and be able to sponsor the NCRS 2022 conference. So this talk will be about application of PRA approach in nuclear power and space sectors. So where I will be touching upon what is PRA and the main objectives of PRA and how the probabilistic risk assessment benefited the nuclear industry and the space industry, and what is the
Yeah,
framework.
just a quick interjection. Would you please tell me how many slides you will be able to cover in this? We
Yes,
have
sir.
roughly around 10 minutes.
Yes, sir. So I'll be able to cover all slides. I have about 15 slides.
Great.
Yes.
No problem. Yeah.
So yeah, we'll be touching upon the framework of PRA that is existing in the space industry, and some of the challenges faced by PRA analysts while developing the space PRA models, and a little bit about the perspective of how and why PRA is useful for space missions. So as everybody knows, the main objective of PRA. So PRA is a comprehensive, structured, and quantitative analysis technique to identify and assess risks in any complex technological systems. Basically, the three questions asked by PRA are: what can go wrong, what are the consequences or end states, and how likely is it? So often these three are called as risk triplets. And the main objective of PRA is to develop a fully integrated model of the facility and identify all the event sequences that can originate from a variety of initiating events and be able to determine their frequencies and consequences. So a PRM model consists fundamentally, it comprises of event trees and fault trees, wherein the event sequence progressions are modeled using event trees, which depict the success and failure of various safety systems and support systems required to mitigate the consequences of initiating event. And fault trees are used to compute the unavailability of these systems. It's basically a top-down detective approach that models the undesired state of a system and tries to identify all possible basic faults, including component failures, cable failures, and human errors that can result to this undesired event. So this is just a visual depiction of how an event tree looks like for an initiating event in a nuclear power plant, and on the right side, how an event tree looks like for an initiating event in a spacecraft. The event tree starts with an initiating event, and it models basically the plant response. These blocks are function events, and the PRA basically analyzes the success and failure of different function events, and it models different function events and associates the consequences depending on the failure of the function events. And within these function events, the unavailability of the safety systems are computed with the help of fault trees, and the fault trees are connected to event trees. So this is basically the visual representation of event tree in a nutshell. While the structure of the event tree looks similar between nuclear industry and the space industry, there are a lot of specific aspects and specific modeling approaches that need to be taken care, especially with respect to the nature of the space mission, and since it is a phased modeling approach, and also in terms of the um, definition of the end states, it varies significantly. So the main goal of PRA is to improve the safety and performance of any system or a facility in a cost-effective manner. And there are a number of software tools that are available to carry out PRA study. With Risk Spectrum PSA is a well-known software, and CAFTA and Sapphire. These three are majorly used softwares for PSA modeling. I would like to state that NPCL has been using PRA techniques for quite a long time and is also using Risk Spectrum PSA for quite a long time. And within the space industry, ISRO has recently started to use PRA techniques for their human spaceflight missions, and they have also plans to apply PRA techniques for their future space missions. And they have also started to use Risk Spectrum PSA. And there has been increasing interest both public and private sectors to undertake PRA studies and be able to take the benefit of PRA studies. Now, a little bit about the PRA's historical perspective. PRA has its roots from aviation industry as early as in the 1960s, and following that, NASA began to use PRA methods in 1967 after the Apollo 1 cabin fire, and then switching to the nuclear industry. WASH 1400, as everybody will be familiar in the nuclear fraternity, that WASH 1400 was the first full-fledged application of PRA that predicted accident scenarios like the 3 Mile Island accident, which occurred in 1979. And later, PRA started to gain a lot of momentum in the space industry, especially after the Challenger accident in 1986 and the Columbia accident in 2003. And over the course of years, PRA methodology started to mature significantly, and it started producing highly useful results on design and operational improvements. Now, in the nuclear industry, PRA is mandated by all nuclear regulators worldwide, and it has become integral part of safety assessment, especially post Fukushima. And just to give you an idea, like nuclear industry being the primary industry that is using PRA most often, followed by space industry, there are other industries that are also actively using PRA studies, like the oil and gas industry, chemical industry, transportation sector, aviation industry, and marine industry as well. Okay, I'll not touch upon, I'll not describe in detail about the evolution and advancements here, but just to start with, how PRA has started very primitively in the 1950s, and then how it has significantly taken shape today. Wherein we can see that post-Fukushima has mainly played a role in increasing the scope of PSA. So modern PSAs have broader coverage of initiating events. It includes all possible external events that can occur at a site, including the individual units risk and the site level risk, multi-unit risk. And then currently PSAs also address combinational events like seismic event and tsunami together. And then it also addresses induced events, for example, seismically induced internal fire and flooding events. And then it also takes into account in-depth treatment of organizational factors in addition to the human errors that are typically modeled in PRA. And now PRA studies are used for a lot of risk-informed and performance-based applications. And currently, level 3 PRA gains more importance post-Fukushima. So this is the typical framework that is followed in the nuclear industry. Basically, PRA has 3 levels: level 1 PRA, level 2, and level 3 PRA. So the main goal of level 1 PRA is to identify sequences that can result in core damage. So the level 1 PRA provides insights into strengths and weaknesses of safety systems and emergency operating procedures in the plant. And then the output of level 1 PRA feeds into level 2 PRA, where the responses of containment systems are basically analyzed. And the objective of level 2 PRA is to quantify the large early release frequency. And level 2 PRA provides insights into strengths and weaknesses of containment systems and on-site accident mitigation and management measures. And the combined input of level 1 and level 2 PRA actually is used for level 3 PRA. It's basically a off-site risk assessment. So it evaluates the frequency and magnitude of radiological consequences to public, environment, and society. Now, just to
finish your presentation in another 5 minutes, okay?
Yes, sir. So now, some of the key benefits brought by PRA in the nuclear industry are it has led to the development of station blackout rule, then backfit rule. It has also brought a lot of changes to plant licensing basis, maintenance rule, fire protection rule, and so on. Now, this slide tells about the vital role of PRA throughout the life cycle of a nuclear power plant. It helps right from concept design until decommissioning. So there are various goals of PRA in each of these stages, and in the interest of time, we will not discuss this in detail. Now, moving the perspective to space industry, the definition of risk it is important to understand the risk in space industry. As everybody knows, space missions are very risky endeavors with unique hazards, risk, and technical challenges. So risk can happen anywhere during the design, build, transportation, or launch stages of a spacecraft, or during its operation in orbit. So typically, depending on the severity of failure, the consequences can lead to loss of mission, loss of vehicle, or sometimes a loss of crew for a manned mission. The other consequences can be like it can result in a degraded system performance or loss of critical infrastructure or assets. And of late, the concept of space safety also extends to planetary protection, meaning how PRS can be used to assess the protection to Earth and protection to other celestial bodies, and also how PRA can be used to assess the risk from space debris and long-term environmental effects of space operations. Now, typically the benefits of PRA for space missions are it can be used to validate conceptual designs like crew exploration vehicle or launch abort systems or robotic landers. And it can be used to evaluate alternate design concepts, design modifications, and upgrades. It can also be used to fulfill safety compliance for special missions like the Mars sample return missions or any mission that is carrying nuclear payloads. And PRA is powerful. It can evaluate the impact of proposed engineering changes, and it can enhance system engineering design and reliability. Now, just on the right side, the experience from NASA PRAs state that developing a PRA model as early as possible and integrating that with the system design and engineering helps to increase the reliability and availability of the overall space missions, and it can benefit the space mission in a more effective manner. Now, there are several international organizations and space agencies that are defining the type of space missions that require a mandatory PRA study. Some of the examples are when a human is sent to space. For example, for any crewed manned mission, PRA is mandatory. Then when any launch vehicle is carrying nuclear materials, then the risk assessment needs to be supported by PRA. It is also required by the UN Outer Space Agency, and also it's also a requirement from the IAEA. Now, when you are demonstrating any novel technology or a first of a kind space mission, then PRA is vital. Then we already covered the role of PRA for planetary protections. So, and NASA also says that regardless of the nature of the mission, if the life cycle cost exceeds $1 billion, then a PRA study is required. And as you know that safety assessments require only a small fraction, approximately less than 1% of the total mission budget. So this must be seen as an essential investment in the industry to undertake PRA studies. Now, what are the different challenges, some of the most important challenges contemplated by PRA analysts in the space industry. First of all, there is only limited or no specific guidance on special PRA areas like the initiating event definition or scenario modeling or data analysis. And secondly, the component failure data sources remain proprietary to national agencies, and only limited guidance or information is available in the public domain. There is no common knowledge base due to uniqueness of space missions, obviously due to the choice of technology and the nature of mission, the objectives and the mission profile. So this makes it very difficult to develop a common knowledge base. And then the technology drives the scope of PRA in the space industry. So that makes it difficult to undertake a PRA study. Then space PRA models are largely developed based on experience gained from previous missions and expertise of team comprising PRA practitioners, space scientists, and mission designers. There are other challenges as well, like how to understand system complexities in a dynamic environment, and how to validate the coverage of all types of hazards and IEs across all mission phases. Then how to do a phase-wise modeling, and what is the event-tree modeling strategy that I follow, whether I follow a large single event-tree modeling approach or a multiple event-tree approach. Then what are the different types of success criteria that has to be considered across different mission phases. Then data analysis, and how to model software failures, structural failures, and how to integrate human errors into the model, especially when the space mission has fully autonomous crew module. How to capture these specific aspects in a PRA model. Then then about the PRA project management itself. So how to manage a large scale PRA project when different centers are involved or different departments are involved in building up a PRA model. How to ensure that the model integration is carefully done and be able to provide a meaningful result, and how to carefully interpret results. So these aspects still remain a challenge in space PRA models. Now, to just say that the PRA practitioners and space mission design team should work together and develop PRA models with due consideration of specificities of the mission to build a robust PRA model. This is very important. And I just have 2 more slides, sir. Just as concluding remarks and perspectives, we all know how the PRA for nuclear power plants have evolved considerably since 1970s. The modern PRAs have very broad coverage of initiating events. Like it includes all possible external events that can happen in a site. It captures the site level risk. It analyzes multi-unit risk. It integrates the human errors and associated dependencies in the model. So basically, PRA gives a holistic risk perspective for a nuclear facility. Still, PRA is used as a complementary study for the traditional, along with the traditional deterministic studies in the nuclear industry. And insights from PRA have helped to strengthen several regulatory policies on safety assessment. It has brought numerous benefits, such as the development of station blackout rule, changes to plant licensing basis, fire protection rule, and so on. Besides safety demonstration, PRA is used today to support a lot of useful applications like the significance determination process, the risk-informed optimization of plant technical specifications, basically the allowed auto HTM and test interval optimizations. PRA has also helped to streamline the maintenance activities, and it has also helped to be able to monitor the real-time risk of maintenance activities in the plant. It also helped to identify critical pipe inspection of critical pipe segments in the plant and so on. There are lots of benefits. Post Fukushima, PRA has increasingly gained importance in safe design and operation of NPPs worldwide. With respect to the space industry, the importance of safety and reliability demonstration for space missions is growing rapidly, more than ever. And increasing interest in development of PRA models in the global community based on harmonized safety regulations and standards. So several international organizations and agencies such as the ISO, NASA, European Space Agency, and the JAXA, they have published a lot of safety standards, technical standards, and guides on risk assessment, and especially focusing on when a PRA is mandatorily required. And then there are a lot of general framework for PRA studies, especially NASA has published a detailed PRA methods guide and safety systems handbook, but still the development of PRA models in the space industry has been very challenging, mainly because there are no standalone guides on specific PRA tasks like the data analysis or the initiating event analysis and so on. So these have been very difficult to develop due to the technological differences and nature of space missions. So an effective and useful space PRA can be developed with good collaboration between among PRA practitioners, space scientists, and the mission designers. And I would like to conclude that, like in the nuclear industry, PRA must be seen as an important requirement by space regulatory bodies and space agencies to analyze the space mission risk in a holistic manner and gain the numerous benefits of PRA to strengthen safety and reliability of space missions. I would like to thank NCRS for giving me the time to present this topic, and I leave the floor to next author. Thank you.
Yeah, so thank you, Vignesh, for a very insightful work in this sector, particularly the application of PRA in space missions is really challenging and very important considering the risk involved, not only the human risk, but the mission risk also. So before we move to the next presentation, I would like a clarification from our host Sujata ji and Senthil Kumar. As per the schedule, I think this is the last session of today. Am I right?
Yeah, this is the last session, but we are already late in time.
Yeah,
we are
so
behind schedule.
Yeah, so can we extend maybe around 10 minutes so that we will have fruitful discussions? Is it possible?
Sure, yeah, we can go ahead. We'll try to accomplish, but we'll allow 10 minutes.
It is already, yeah, it is already 7:45, and we have just completed only one of it, right?
Yeah.
So with all participants,
yeah,
consent,
we can go ahead. We can go ahead. The only concern is most of them are in office still. They have to go home. That's what.
Yeah, because otherwise I will have to cut some minutes from presentation. So I'm open to it depending upon your convenience.
Yeah, we can go ahead. We'll see as it goes.
Okay, fine, no problem. So with this small clarification, let us move on to the third speaker, Mr. Vikram Gupta. He is presenting his paper on reliability allocation of repairable multi-component system using fault tree analysis and genetic algorithm. So Vikram Gupta, kindly limit your presentation slides and try to finish the talk in allocated 10 minutes time.
Sure, sir. Good evening, sir, and good evening, ma'am. So my slide is visible to you. Hello.
Hello. Yes, it is visible. Yes.
So my name is Vikram Kumar Gupta. I am currently pursuing PhD from Subir Chaudhary School of Quality and Reliability at IIT Kharagpur. So my topic is reliability relocation of repairable multi-component system, which is plate heat exchanger using fault tree analysis and genetic algorithm. So the paper is proposed the reliability allocation method to define and identify the system reliability and availability factors, which is in plate exchanger. So basically, reliability allocation in repairable and replaceable system is very different. So there are the different models in the replaceable system, like delta tau method, but the reliability allocation in repairable system is based only on the availability and unreliability. So engineers are frequently faced a problem with the system that comprises a multiple component system, and to entails a balancing act in order to establish how reliability and availability divided to in subsystem and components. So reliability of the system also needs to be considered with the intermittent availability and constant wear of the system. So the paper discussed the various failure mode in the plate heat exchanger method collected from the various literature reviews, and papers also discussed with the fault tree analysis in failure of plate heat exchanger and optimize the overall cost of the repairable component system using genetic algorithm. So repairable systems already I have told you just subsystem failure rate to the system to fulfill a repairable system availability goal. So all systems are assumed be in series with exponential failure distribution and constant and variable repair rates in the paper. So what is important in the repairable system relocation? So the overall cost of the system can be traded off between replace and repair action. So solution provides optimal policy of decreasing the failure rate of the system at the same time increasing the system reliability and availability goals. So the repairable system comprises a minimal repair or perfect repair, which is as good as new or as bad as old. So depending between those two, the overall custom system can also be decreased. So problem statement and methodology. So what we have discussed in this paper. So estimation of current and future failure property in heat exchanger is required to make a decision for equipment replacement at the right time to eliminate unnecessary shutdown caused by unexpected faults and failure modes. So, in this important way to determine the availability and reliability for the system and subcomponent level. And from this we can operate conclude that there is a replaceable action or repair action can be formed in the heat exchanger. So defects fall. So there are different failure in plate heat exchanger like service failure, mechanical failure, control system failure. And basis on design, process, and environmental failure. So the proposed methodology suggests a combination of a specific method to solve reliability allocation on this paper based on FTA and GA generic algorithm. So there is a software package of FT top event, so which can be designed FTA tree and calculate the availability and reliability of the PHE. So my first step is to define the various PHE plate exchanger failure modes caused by design, maintenance, and inspection. Second, collecting the data for the reliability and availability of various subsystems such as the failure rate, repair rate, and the repair cost currently. So draw the FTA event tree by OR and AND logic gates. Then calculate the top event failure probability and minimum by minimum cut set method, and calculate the top event each event unavailability and reliability and rank them in order. So and optimize the repair cost function based on the availability using genetic algorithm. So this is the common plate heat exchanger diagram taken by the Isaka Private Limited. So there are the different plates which is between the gaskets, and the gaskets is spread between the frames, and all this is combined together the guide bar and the bolt and nut. So this is there is some gap between the plates. Yeah. So why heat exchanger reliability is what various for the heat exchanger reliability in this story. So improved reliability regarding maintenance and better economic performance. So there are 4 main type of system event in analyzed subsystem: normal event and downtime, scheduled outage, and repairing of cleaning, unexpected fault, outage caused by the special order. So basically heat exchanger fails due to mainly different type of issues like fouling, thermal evaporation caused by height fluctuation, and faulty alignments. So probability of all these events together leads to heat exchanger failure. So the next, these are the common failure mode effect analysis, and this is the below root cause analysis, which is taken by the Nuclear Safety Board (OECD). So these are the environmental, design, manufacture, and procedure adequacy are the toppest amongst these failures. And the right one is the failure symptoms and failure category and percentage distribution of failure modes like in subsystem, plate, gasket, guide bar, rubber boot, bolt and slit, E and S frame. So different failure symptoms like leakage, cracking, blocking, faulty alignment, clogging, blocking, loose and bolt. And there's a subsystem and failure category: complete count failure, impaired and partial count failure. So this is the plate exchanger failure fault event tree analysis. So there are the basic 5 basic events and 7 gates, which is divided by OR and AND gate logic. So there are this 7 events and 7 subsystem like a plate bundle failure, gasket failure, guide bar, and bolt and slit, and E and S frame, and then rubber and metal board. So these are the main event which can lead to the plate exchanger failure. So these are the different mathematical formulations. So how we calculate the unavailability and reliability from the fault tree event analysis. So from the minimal cut set, so we can calculate the minimal cut set from the faulty event, which leads to the plate exchanger top event failure, and then calculate the unavailability for each event and for the cut set event, and the unreliability for the same. So, and there's the last total cost function, which can be optimized the genetic algorithm. So this is my analysis. Cut set and implementers, they are the different gates and there are different cut sets. And we know cut sets chooses to be 1, 2, 6, 3, 4, and 3, 5. And there are the event probability, failure probability is given. And these are data, lambda, failure rate, and tau minimal TR. And this is the QI for event inavailability. And for the top event availability, the FTS given is this QS. And then below table is shown as the availability for each event for the cut set event, which is important for the plate exchanger failure, and rank them in order according to cut set event. The same is calculated the unreliability based on the event subsystem and rank them in order, and the repair cost and total cost. So the result, yeah. So we have discussed all these methodology and calculations and the result. So plate exchanger evaluation model involving the failure mode based on these failure mode and root cause analysis. So the faulty alignment, leakage, and cracking is added to a FTA model as a basic event. So for the minimal cuts event, it reveals that the main basic, these are the main basic events, and the plate exchanger failure probability and failure rate for the top event are 0.00364 and 0.07 respectively. And the cuts event, the cut set event 1 to 6 is a major event contribute to the failure of plate exchanger caused by maintenance section and design issues. So most hazardous branch is connected with the gate 2 and gate 6, which includes the mechanical component. And the probability of top event early termination for the PHA is calculated by FTA is 0.34%. So these are the line plot for rank in order for the availability for the cut set event. And this is the diagram for failure rate versus repair system. Increasing a failure rate, so repair for the repair action, it is increasing or decreasing with respect to it. So this is my another descriptive statistics and significance fit for the I performed with the availability regression analysis. So the mean availability, mean reliability, cost, optimal total cost, and the top event and failure probability and top event failure rate. So and the sorry. So this is the diagram which is shown the optimized genetic algorithm. So which has optimized the total repair cost based on the unavailability. And this diagram is versus total cost versus unavailability and unreliability. So what is concluded from this proposed methodology focus on a PHD maintenance, so the influence are availability and reliability rather with respect to optimization of repair costs. So unavailability of event found to be maximum, that is 74%. The heat exchanger failure probability caused by faulty alignment and leakage and cracking is high, while PHE considered clogging, blocking, and loosen bolt is about to 8% and 6%. So considering maintenance and inspection in industrial application can guide establishment of cleaning scheme and design of heat exchanger. So unreliability importance from this paper has also ranked as based on FTA, and event 1 to 6, that is 71%, 0.2%, 22%, 28% found to be most unreliable event caused in plate, gasket, and frame. The repair cost shows the decreasing trend from the event 6 to 1 and suggested to take replacement action through the optimal allocation based on the repair cost. So optimal cost found to be in 1304 in Indian rupees, which is 1/3 of the total individual cost of the subsystem repair. And the genetic algorithm gave the optimal cost point at minimum unreliability and availability, and proposed solution inferred that event 1 to 6 once occurred, the object corrective action should be taken for the PHE. From this one can conclude the PHE will achieve maximum availability and reliability. Conclusion, the result obtained, so these are the feature, these are the main conclusion from the this analysis. Result obtained have great potential for even future safety research as well in PHE process, because we have discussed right now currently design and inspection and issues. So which we can use this in a PHE process, often in high temperature and pressure. So FTA method is suitable for improving not only the analysis PHE process, but also simply suitable for other issues such as inspection, design, and reduce the damage of health of employees and material and technician. So it to provide a way reduced to future losses, and this aims through the optimum maintenance policy, like continuous maintenance, condition-based maintenance, and corrective maintenance, and we can be based on unavailability and reliability. So all major failure types is considered, including heat exchanger breakdowns, following leakages, and this can reduce or even eliminate the need for total unit shutdowns required for cleaning. because we have known that plate exchanger is very indispensable in equipments which has stopped the production process. So we can also discuss, we can take like a system approach and heat exchanger network analysis, local parameter, SPR and cost. So this case 21st a proposed approach to find the weak point in PHE and emphasizing small.
Yeah, so thank you, Vikram, for your insightful presentation. And because of lack of time, I need to rush through this presentation. So with thanking you, I invite the next speaker, Sri G.S. Bhatia, who would be presenting his paper on estimation of liquefaction potential of a alluvial soil site, a reliability-based approach.
I could not see
Mr.
the author
Bhatia,
log. I could not see the author logged in. Is he there?
Okay, so with that, I will take another 30 seconds. If from audience, any other author is present to this paper?
Sir, I am the next author. I'm Kirtana from SCRC. Can I proceed, sir?
Yeah, please go on. So let me just introduce you. Ms. Kirtana and Sri Hari Krishna has prepared a paper on probabilistic modeling of non-Gaussian wind-induced peak pressure on a model of tall building. So with this brief introduction, let us hear from Ms. Kirtana.
Yeah, good evening, everyone. So the paper that I'll be presenting today on probabilistic modeling of non-Gaussian wind pressure on a tall building. The paper has been authored by myself, Kirtana from CSIR SCRC, Structural Engineering Research Center, and Dr. P. Hari Krishna. So this is the outline of my presentation. So I'll be touching upon the need for the study, the scope of the present study, and the experimental data based on which the probabilistic analysis has been carried out and the results. So all the civil engineering structures are basically bluff bodies, wherein the sharp corners act as point of flow separation as indicated in this figure. And in the separated regions, separated flow separated regions and the wake, the pressures are going to be negative in nature, and they are also going to be non-Gaussian in nature. And the structures are subjected to boundary layer flow characteristics as developing on Earth's surface. So that would add to the overall complexity of the problem. So the wind action on the structures are manifested as pressures, and the multivariate pressure fluctuations acting on structures are certain regions. It is highly localized in nature where peak pressures can be developed. And why it is important is because it could lead to failure of roof cladding or facades or glass cladding of high-rise building. So both low-rise and high-rise buildings are prone to failure due to the peak pressures that are developed in local regions. And appropriate evaluation of peak factors or peak pressures are one of the key aspects of performance-based design. So basically the building envelope or the cladding that we design have to withstand the wind loads, for which we need to accurately estimate the wind pressures, including the peak pressure. So to further show the importance of the present study, so we can see the failure of glass cladding during gusty and extreme wind events. So during Cyclone Varda in Chennai and abroad. So cyclone and hurricane are almost similar, with the names being different and different regions. So we could see similar damage to glass cladding under extreme wind events. So this shows the importance, like why we need to study the peak pressures, especially in the flow separated regions of low-rise and high-rise buildings. So, and the characteristics of that pressures are going to be non-Gaussian in nature. So if somebody adopts a conventional Gaussian-based approach or framework for evaluation of peak factor, then we would be underestimating the load. So the design tends to be unconservative. And such estimation of peak factors for wind-induced pressures on structures still continue to be an active area of research, with the failures still being, we are observing many such kind of failures for structures designed based on Gaussian framework. So there are two approaches. Basically, one is parametric and another one being non-parametric or data-driven. So in the parametric approach, we take the peaks, selective peaks from the data, and it is fitted to an extreme value distribution. And the peak factor is estimated for a defined fractile level of probability of non-exceedance from the CDF. Wherein non-parametric or data-driven approach involves use of higher order statistical moments either from the data or extremes, and then within the analytical framework we evaluate the PDF and CDF, and to get the peak factor we take a particular fractile of probability of non-exceedance. So for the parametric models, so a huge or humongous data requirement is there. So because the prediction of extremes are dependent on the amount of the quality data that we have. So a lot of studies have been carried out in the literature on the parametric models. And they have also seen that it was not possible to use a single model to capture both the bulk and tail portions of the extremes. So a combination of models are also being used. So among the non-parametric models in the non-Gaussian framework, so Hermite polynomial models are being widely used and their variance. So this slide shows the evolution of the Hermite polynomial models and how from the initial proposal, it has come to a stage wherein it could predict the non-Gaussian wind-induced peak pressures on structures. So the present scope of present study involves evaluation of peak factors on a tall building model for 3 different angles of wind incidence. So for wind normal to two faces of the structure and a skewed wind direction. And the models that we would be adopting are the basic Hermite polynomial model and its improved variants. And the comparison has also been made with the experimental data. So I would just briefly touch upon the basic premise of Hermite polynomial model. So it is a nonlinear transformation that converts the non-Gaussian process to a Gaussian process. And there is a nonlinear transformation that is involved. So that we are expressing in terms of a third order polynomial. So that is why it is basically called a Hermite polynomial model. And the coefficients of the Hermite polynomial are dependent on the skewness and kurtosis. So higher order moments of the process. And through that, we evaluate the peaks of the process. So, and the probability density function and CDF as would be given in the next slide. So PDF are evaluated through these expressions, and then the peak factor, these are the expressions for the peak factor through this approach. And finally, how do we arrive at the peak factor is through this. So we know the standard deviation and the peak factor and mean. So through that, we estimate the extremes in the process. So for the experimental investigation, so we have taken the wind tunnel data, wherein we have made a scaled down model of a 270 meter tall building with a rectangular plan shape and with pressure measurement at 5 different levels. So this was the layout of pressure tap at a particular level. The pressures were measured at a higher sampling frequency of 650 Hertz for a duration of 24 seconds, and multiple trials were taken. So total data that was available was for an 18-hour full-scale duration. From this, peaks were picked. And so this shows the view of the wind tunnel facility that we have at CSIR SCRC. And this shows the model of the building, the shown building, for 2 different angles of wind incidence, 0, 90, and also 45 we have covered. So, and the measured pressures have been converted to a non-dimensional pressure coefficient. So we basically divide the pressure with the dynamic pressure so as to get a non-dimensional pressure coefficient. So that would be same for the model and the prototype or the full scale structure. So, and this shows the typical time history of pressure coefficients from a particular point. So one pressure tap. So after flow separation, this is the kind of time history that we would be getting. So it is clearly seen that at certain instantaneous points, we are getting a spike in the pressure coefficient. So this kind of pressures are that cause damage to the glass cladding. And also if we are looking at the probability density function, so from the data, we can see that it is deviating from the Gaussian nature as shown in this green curve. And the skew higher order moments are also significantly deviating from the values for the Gaussian distribution. So, and this is the contours of skewness and kurtosis. So we can see the values touching, kurtosis values touching about 10 in certain regions. And when we are using Hermite polynomial models, we also need to make sure that the data points are lying within the effective region of applicability of the model. So all the pressure tap information we have seen, and we have ensured that they are fitting in the zone of applicability of Hermite polynomial model. So, and the certain points that are falling outside are corresponding to those in the windward phase of the building where positive pressures will be there, and the estimate of peak pressure is already on the conservative side. So the suction pressures or the negative pressures are of more concern to us, and those data points are falling within the effective region of applicability. So, and the procedure goes like this. So we standardize the data. So we divide by the, we subtract the mean from the data and make it a unit variance. So variance is made equal to 1. And then we evaluate the coefficients of the Hermite polynomial model. And then PDF and CDF of the data is obtained and plotted. So like this. So for a typical 0-degree case, so the three Hermite polynomial models that we have considered and the data as well as the Gaussian based PDF.
Sorry to interject you, but we need to rush it up. So
yeah, just 2 minutes.
Sure, yeah.
So 0 and 90-degree case, we have also made a comparison with the data from experiments. So from experiment for a 2-second window, we have picked peaks from each window and that is plotted here. So we can see finally the peak factors evaluated. I'm just showing the result for one particular level. So the estimate from the Hermite polynomial models are on the conservative side compared to that of the experimentally observed values. And we have also made comparison with other model-based evaluated peak factors. So Hermite polynomial model with its improved variance have been observed to give a conservative estimate of peak pressures on the surface of a tall building. So I would like to conclude my talk with this, and I would like to acknowledge my colleagues at Wind Engineering Laboratory. Thank you.
Yeah, thank you, Dr. Kirtana. Actually, it's a very beautiful and very elaborate work that you have done. I'm really sorry because of the time pressure. I could not, do justice to your presentation and your work to be presented. And I also apologize to other speakers whom I have to interject and cut short the discussions. So with this, I think we are coming closer to our scheduled task. The last task is question and answer session. So maybe we can take a couple of questions from audience.
Probably one for the last presenter, Kirtana, can I ask?
Yes, sir.
Yeah, please go on. Senthil,
yeah.
Go on.
How are the building specific parameters included in the model?
What type of building specific parameters, sir?
Because this model that you have demonstrated is not a generalized, it will be specific to a model, to a building.
No, sir. Actually, the model is a generalized model. We are fitting the data from our experiment onto the model.
I see.
So
because
only,
the buildings that you show are all totally different types of curvature, and civil structures were different. but I was only asking how do you incorporate these type of differences into the model, or where is it addressed?
So the effect of geometry will be realized in the pressures that are developed on the surface, sir. So when we are doing the wind tunnel testing, so this geometry, depending on the geometry, the pressures that we measure will be, pressures are realized accordingly. So there's nothing specific that we need to do to take care. As long as we are doing the scale down model of the structure properly for wind tunnel testing, the pressures that are developed are representing the actual phenomena.
Okay. And one more thing, how do you, is there a way to validate the results?
So
I think
we
it will be
have,
difficult.
for full scale, it will be difficult, sir, because we don't have much of measurements. But for low rise abroad, they have a building like this, a cube building, from which they are measuring the pressures. So that is like a benchmark data that is available for comparison. But for tall buildings, no, sir. Wind tunnel, to some extent, it can help.
Okay, thank you.
Thank you, sir.
Any other question? Quick question. So if there are no questions from audience, I have one question to Mr. Vignesh. Hello.
Hello. Yes,
Vignesh,
sir.
are you
I'm
there?
here. Yes, I'm here.
Yeah, just wanted to know what are the typical risk metrics that is being used for PRA for space applications. Like we are using CDF and LERF for nuclear sector. Is there a typical risk metrics that are being used? You have mentioned about some handbook which is developed by NASA. So could you find some typical risk metrics that they use? Design of a spacecraft is one thing, and the mission success is another thing. So it's a full spectrum. Can you just elaborate on that?
Yes, sir. Thanks for this question, because in the nuclear industry, we are always familiar with the two risk metrics, CDF and LERF, right? So in the for space missions, like it is very mission specific, the risk metric that you want to look up. But the typical risk metrics are, let's say if you are sending a satellite to space without any humans. So the typical risk metrics will be loss of mission and loss of vehicle assets, or if the satellite or is supposed to do some functions, or if it is supposed to carry some important scientific instruments, then you can add one more risk metric called as loss of scientific data. So the three typical risk metrics in this case will be loss of vehicle, loss of mission, and loss of scientific data. But if you're sending humans to space, then the most important risk metric will be loss of crew.
Okay.
So loss of crew and vehicle, loss of mission factors into account. These three are the important risk metrics that we look in the space PRA.
Yeah. So
And
thank you
since
for
the
that
model, yes, sir. Since
Yeah.
the model is actually supposed to be built mission specific, and also there are several phases involved in the mission. For example, there are ascent phase. The launch vehicle basically travels to a space, right? So there is an ascent phase involved, and then there is also entry into the orbit phase. Then there is orbital phase. And then, for example, if it is a crewed mission, then you have to capture the risk during re-entry phase, and then during the return phase.
Yeah.
And it's a phased mission modeling approach. And but these are the three typical risk metrics involved: loss of crew, loss of vehicle.
Yeah,
and
it is quite interesting as well as quite challenging in absence of any standard PRA done for such kind of applications. So I do
Yes.
appreciate your presentation and your sponsorship
Thank you, sir.
for this program, and I thank all the participants for patiently being with us for this session. And by thanking, I'm handing over to Mr. Senthil Kumar for a closing ceremony.
Thank you very much, Dr. Solanki, for organizing and conducting this technical session and summarizing and allowing us to interact also. So on behalf of the organizing committee, we thank you for the session. Thank you very much.
Okay.
Over to Dr. Sujata, madam. What is the status of the other room?
Once again, sir, let me check. Completed. Okay.
Ma'am, we have completed, ma'am.
Yeah, okay. Thank you, ma'am. Thank you so much.
Okay.
Okay, then final announcement, if any, you can make, madam.
Okay.
Or Dr. Vardhe, Dr.
Vardhe sir is also there. Yes,
You
he's
are on
there, sir.
mute, sir. You have to unmute and talk.
Till 1 minute. You have to make one announcement that all chairmen will have to give a report, small brief, paper 1, 2, 3, 4, and so that we can select the best paper, because we have this best paper award. It will help chairman's reporting and all that. So Dr. Solanki, thank you. You'll have to give one report also on whatever session you had. Thank you.
Okay.
Okay then.
Thank
now
you, sir.
who is the in charge of this room? I think they can.
Thank you, sir. So now we are at the end of the day 1 of the 5th NCRS in 2022. So let us join tomorrow for the second day schedule. So the links have already been shared, and please remember the same link can be used, which you had used today for joining the technical sessions. Thank you all and good night.
Good night to all of you. Thank you.
Thank you.
Excellent
Thank you.
work. Thank you.
Thank you.
Thank you all.
In for all good wrong, sir.
Yeah, you can give.
Okay, sir. Thank you, sir.
Thank you.
I should stop the recording.
Yeah, I've also stopped recording. It was,
Yes, sir. Only thank you, sir.
Okay, I think it went on well today. There's no issue.
Yes, sir. Hope we have smooth conduct for the next 2 days.
Yeah.